Imagine a universe so vast, it harbors more stars than there are grains of sand on Earth. This concept only begins to touch on the profound mysteries scattered across the cosmos. From the birth of galaxies to planets drifting silently through space, the universe continues to offer up clues about our origins and the very nature of reality itself. Embark with us on an exploration that challenges everything you know and stirs your curiosity for the wonders yet to be discovered. At the heart of our understanding of the cosmos lies the Big Bang Theory, the leading explanation for the creation of the universe. Supported by an overwhelming body of evidence, this theory paints a picture of a universe that began as a single, infinitely dense point and has since been expanding over billions of years. One of the most compelling pieces of evidence is the cosmic microwave background, CMB radiation. This faint, pervasive glow is often referred to as the aftershock of the Big Bang, providing a snapshot of the universe when it was in its infancy, only about 380,000 years old. Back then, the cosmos was an incredibly hot and dense environment, with atoms unable to form due to the intense heat. As the universe cooled, light was finally able to travel freely, and the radiation we detect today serves as a relic from those earliest moments. The discovery of the CMB was a landmark achievement in the 1960s by radio astronomers Arno Penzias and Robert Wilson. While investigating a persistent noise in their equipment, they stumbled upon the faint but ubiquitous radiation. Their discovery provided tangible evidence that the universe had not always been as we know it today. It had a beginning, one that was hot, dense, and ever expanding. This breakthrough confirmed that the universe was not static but was evolving and growing. The CMB's discovery was just the beginning. Since then, scientists have delved into the fluctuations found within the radiation, tiny variations that reveal crucial details about the universe's early conditions. These subtle ripples represent the seeds of structure in the cosmos, which would later grow into the galaxies, clusters, and vast cosmic filaments we observe today. By studying the CMB in greater detail, cosmologists have been able to measure the expansion rate of the universe with remarkable precision, allowing us to calculate the relative amounts of dark matter, dark energy, and ordinary matter that compose the cosmos. The CMB, in this sense, serves as a cosmic echo, providing us with an unprecedented glimpse into the universe's origins and helping us better understand our place within it. As scientists continue to study the fluctuations in the CMB, they continue to unlock new insights into the universe's age, its composition, and its evolution. With every new discovery, we edge closer to answering some of the most profound questions of existence. What was the universe like in its earliest moments? How did it evolve from a singular point to the vast expanse we see today? And perhaps most intriguingly, what mysteries still lie hidden within the deepest recesses of space? Another revolutionary concept that enhances our understanding of the cosmos is the theory of inflation. This theory proposes that moments after the Big Bang, the universe underwent a period of rapid expansion, growing exponentially at speeds faster than the speed of light. This brief but intense burst of growth, known as inflation, reshaped the universe, smoothing out irregularities and laying the groundwork for the large-scale structure we observe today. Inflation theory helps explain why the universe appears so homogeneous and isotropic, meaning it looks the same in every direction. Without inflation, we would expect to see substantial temperature and density variations across the cosmos. But as we observe through the CMB, the universe exhibits remarkable uniformity on large scales. This uniformity, according to inflation, was the result of quantum fluctuations during the rapid expansion. These fluctuations, tiny variations in density caused by the inherent uncertainty of quantum mechanics, were amplified as the universe expanded, eventually leading to the formation of the galaxies and clusters of galaxies we see today. This connection between quantum mechanics and the large-scale structure of the universe is a profound insight. It alters the way we view the cosmos, showing us that the very building blocks of the universe, galaxies, stars, and even planets, were shaped by forces that operate on both the smallest and largest scales. These quantum fluctuations acted as the seeds of future structures, and over billions of years, they grew into the vast, interconnected cosmic web that makes up our universe today. The implications of inflation theory are far-reaching. Not only does it provide a coherent explanation for the universe's large-scale structure, but it also opens the door to deeper questions about the very nature of space and time. Could our universe be part of an even larger multiverse? Could inflation have occurred multiple times, giving rise to countless parallel universes? These questions, once purely speculative, are now subjects of serious scientific inquiry, thanks in part to the framework laid out by inflation theory. Together, the Big Bang Theory, the discovery of the CMB, and the theory of inflation present a powerful narrative about the origins and evolution of the universe. They offer a tantalizing glimpse into the past, revealing a universe that began in a hot, dense state and expanded rapidly to become the vast, complex structure we see today. But they also inspire even more questions that continue to drive our curiosity and fuel our desire to understand the cosmos on a deeper level. As we look further into the universe, we are reminded of the immense scale of space, where every star, every galaxy, and every black hole tells a story of creation, destruction, and transformation. The universe is constantly evolving, revealing new mysteries and offering new insights. With each discovery, we come closer to understanding not only where we came from, but where we are headed. And as we venture further into the cosmos, we may find that the answers to the universe's most profound questions are closer than we think. Inflation theory opens up an intriguing door to understanding the very nature of our universe, prompting bold questions that stretch the boundaries of what we consider to be reality. It proposes that beyond the limits of our observable universe, there may exist other regions, perhaps even entire universes, that lie outside the reach of our instruments and observation. This concept, often referred to as the idea of a multiverse, challenges the traditional, narrow understanding of reality that we have held for centuries. It invites us to consider a reality far grander than what we've known and pushes the boundaries of human curiosity, encouraging deeper exploration into the fundamental nature of existence itself. It compels us to ask, what are the mechanisms that gave birth to our universe? And are there other universes, possibly with entirely different laws of physics, existing in parallel? Moving to the origins of the universe, nucleosynthesis, the process by which elements are formed through nuclear reactions, was a key event in the formation of our cosmos. This process unfolded in the moments after the Big Bang, during the early stages of the universe, when it was an incredibly hot and dense environment. During these first minutes, the conditions were ripe for nuclear reactions to take place. Protons and neutrons, which are the fundamental building blocks of atomic nuclei, came together to form the lightest elements in the universe, primarily hydrogen and helium, along with trace amounts of lithium and beryllium. This period is commonly referred to as Big Bang nucleosynthesis. As the universe expanded and began to cool, these light elements started to dominate the cosmic landscape. Approximately 75% of the ordinary matter that would make up the universe was hydrogen, with helium making up around 25%. The elements formed during this critical time laid the foundation for the future development of stars and galaxies. Over time, these light elements would eventually fuse together under intense heat and pressure inside the interiors of stars, leading to the formation of heavier elements. The process of stellar nucleosynthesis would become crucial for creating the elements necessary for life as we know it. Stars formed from these primordial materials, and as they ignited, they began their own process of nucleosynthesis. Within the cores of stars, hydrogen atoms fused to form helium, releasing vast amounts of energy. As stars aged, they went through a life cycle that saw them producing progressively heavier elements such as carbon, oxygen, and iron through nuclear fusion. When massive stars reached the end of their lives, they would explode in cataclysmic events known as supernovae, dispersing these newly formed elements throughout space. This enriched the interstellar medium, contributing to the formation of future generations of stars, planets, and ultimately life itself. The cycle of stellar nucleosynthesis and the recycling of elements is a key process that has shaped the universe. It is a dynamic and ongoing system that continually generates the building blocks for new stars, planets, and even life. Without it, the diverse range of chemical elements that exist in the universe today, elements essential for the existence of life, would not have formed. Nuclear synthesis, in this sense, is not merely a process that forged the elements of the cosmos, but also set into motion the complex and extraordinary processes that gave rise to everything from galaxies to planets to life forms like ourselves. One of the greatest mysteries in modern cosmology is dark matter. This elusive substance, although invisible to our eyes and undetectable through electromagnetic radiation, seems to account for roughly 27% of the universe's mass. Its presence can only be inferred through the gravitational effects it has on visible matter, such as galaxies and galaxy clusters. Despite its mysterious and intangible nature, dark matter plays a crucial role in the structure of the universe. It acts as an unseen scaffolding, shaping and guiding the formation of galaxies and large-scale structures throughout the cosmos. Without the gravitational influence of dark matter, galaxies and other cosmic structures would likely fly apart as they rotate because the visible matter within them doesn't have enough mass to hold them together. Dark matter's influence is profound. The speeds at which galaxies rotate should, according to Newtonian physics, cause their stars to be flung out into space. But instead, galaxies remain intact. This suggests that a substantial amount of undiscovered mass is holding them together. Moreover, dark matter's distribution is essential for the clustering of galaxies. Regions of the universe with higher concentrations of dark matter lead to denser concentrations of visible matter, forming massive clusters of galaxies. This phenomenon is crucial for understanding how the universe evolved from the hot, dense state it was in shortly after the Big Bang to the sprawling web of galaxies that we observe today. Without dark matter, the cosmos would be drastically different. It would feature fewer galaxies and a far more chaotic arrangement of cosmic structures. Despite its immense importance, dark matter continues to elude direct detection. Numerous experiments, both on Earth and in space, are underway to try to capture dark matter or at least gain a better understanding of its properties. Some scientists speculate that dark matter may be composed of particles we've yet to discover, while others explore alternative theories of gravity to explain the effects attributed to it. Every new discovery brings us one step closer to unraveling the mysteries of the universe and understanding our place within it. The life cycle of a star, a story written in the very fabric of space-time, is a fascinating journey that begins in a stellar nursery. These nurseries are vast clouds of gas and dust, where the seeds of stars are born. Under the influence of gravity, these clouds collapse and begin to heat up, igniting nuclear fusion in their cores. Thus begins the long and intricate life of a star, which will go through various stages, each marked by dramatic changes in temperature, size, and luminosity. The evolution of a star is a journey that can span billions of years, ultimately ending in a spectacular death that may involve the creation of black holes, supernovae, or planetary nebulae. Through this life cycle, stars not only generate the energy needed to support life on planets, but also produce the very elements that make up the physical universe, from the hydrogen in our bodies to the iron in our blood. The death of stars is just as crucial as their birth, for it is through their explosive ends that the raw materials for the next generation of stars and planetary systems are scattered across the cosmos. However, not all stars follow the same path through their existence. Their size plays a critical role in determining their destiny. For instance, red dwarfs, the smallest and faintest type of star, possess an astonishingly long lifespan, stretching across trillions of years. Unlike their larger counterparts, red dwarfs burn their hydrogen fuel at an incredibly slow and steady pace, often remaining stable for vast eons. Their steady rate of fusion ensures that they burn their fuel slowly, allowing them to survive for time spans far beyond the lifetimes of other stars. In the end, these stars will evolve into white dwarfs, small and dense remnants of their former selves, marking the quiet conclusion of their celestial journey. In stark contrast, massive stars follow an explosive and dramatic life cycle. They burn through their hydrogen reserves much faster than red dwarfs, thanks to their immense gravitational pressure and incredibly high temperatures. This rapid consumption of fuel triggers a series of intense transformations as the star fuses progressively heavier elements at its core. After a relatively brief period as a supergiant, these stars reach a critical stage in their evolution. When the core becomes predominantly iron, the process of fusion can no longer sustain the star's energy output. At this point, the star undergoes a catastrophic collapse, leading to one of the most violent and spectacular events in the universe, a supernova. The supernova explosion not only scatters the outer layers of the star across space, but it also leaves behind a dense, compact remnant. Depending on the mass of the original star, this remnant can become either a neutron star or, in the case of particularly massive stars, a black hole. These remnants are not merely the end of a star's life. They are essential to the universe. The materials left behind by these catastrophic events contribute to the formation of new stars, planets, and potentially even life. While red dwarfs and massive stars represent two extremes of stellar evolution, they illustrate the incredible diversity within the cosmic life cycle, highlighting the complex processes that govern the evolution of stars and the broader universe. The journey of a star's birth is nothing short of a cosmic marvel. It begins deep within a nebula, vast clouds of gas and dust that scatter throughout the cosmos. The birth of a star is driven by the forces of gravity as these materials begin to clump together. As the gas and dust come together, certain regions become denser, initiating the process of collapse under their own gravitational pull. This collapse leads to the formation of a core at the center of the cloud, and as it condenses, temperatures begin to rise dramatically. Eventually, the core reaches a critical threshold, where the pressure and temperature are high enough to ignite nuclear fusion. This moment marks the birth of a new star, one that shines brightly as it begins its life cycle. The fusion process itself is transformative. Hydrogen atoms fuse together to form helium, releasing vast amounts of energy in the form of light and heat. This marks the beginning of the star's journey as it becomes a glowing beacon amidst the darkness of space. Meanwhile, the surrounding material, still in the process of collapsing, begins to undergo significant changes. The newly formed star's gravitational pull begins to influence the surrounding gas and dust, causing it to flatten into a rotating disk. This disk, rich in elements, becomes the birthplace for planetary systems. Through a series of complex processes, small particles collide and stick together, growing larger over time. Eventually, these tiny particles form planetesimals, the building blocks of planets. Over millions of years, these planetesimals merge and collide, evolving into protoplanets. These protoplanets then transform into the planets, moons, and other celestial bodies that make up a solar system. Each stage of this incredible journey, from the birth of a star to the formation of planets, reflects the intricate dance of gravity, matter, and energy. It is a testament to the beauty of cosmic evolution, illustrating the constant interplay of forces that shape the universe. The formation of stars and planets is not merely a static process, but rather a dynamic and ongoing cycle that showcases the complexity and wonder of the cosmos. Among the most dramatic and awe-inspiring phenomena in the universe are the supernova, massive, explosive events that mark the violent death of a massive star. To understand how a supernova occurs, we must first explore the inner workings of a star. As a massive star nears the end of its life, it exhausts its nuclear fuel, and the core can no longer support itself against the force of gravity. In the final stages of its life, the core contracts while the outer layers expand, creating a supergiant star. Once the core becomes predominantly iron, fusion can no longer produce energy. This leads to a buildup of pressure within the core, and beyond a critical threshold, the core collapses under its own weight. The result is a shock wave, a powerful burst of energy that travels outward, expelling the outer layers of the star into space at incredible speeds. What we observe as a supernova is the aftermath of this explosion. The consequences of a supernova are just as spectacular as the explosion itself. The explosion disperses heavy elements such as carbon, oxygen, and iron into the surrounding cosmos, enriching the interstellar medium. These elements, which are essential for the formation of new stars, planets, and even life, are scattered across vast distances, allowing for the ongoing cycle of creation. Supernovae can also create nebulae, beautiful and colorful clouds of gas and dust, which, over time, will become the cradle for new stars and solar systems. Beyond their breathtaking spectacle, supernovae also provide scientists with valuable insights into the universe. The light emitted by distant supernovae serves as a powerful tool for measuring the universe's expansion. By studying the light from these far-off explosions, astronomers can learn about the history of the universe, its rate of expansion, and the enigmatic force known as dark energy. These violent and energetic events are not just endings, they are also beginnings, contributing to the continuous cycle of creation and destruction that underpins the structure of the cosmos. Among the most intriguing remnants of supernovae are neutron stars, dense and mysterious objects that result from the collapse of a massive star's core. When a star exhausts its nuclear fuel and undergoes a supernova explosion, the core collapses under its own gravity, causing protons and electrons to merge into neutrons. The result is an incredibly dense object composed almost entirely of neutrons, packed into a sphere that is only about 20 kilometers across, but contains more mass than the Sun. This extreme density means that a single cubic centimeter of neutron star material would weigh approximately 1 billion tons on Earth. Neutron stars possess a number of extraordinary physical properties that make them both fascinating and essential to scientific research. Their surface gravity is about 2 billion times stronger than Earth's, creating extreme conditions that allow scientists to study matter in ways that would be impossible elsewhere in the universe. Neutron stars can also rotate incredibly quickly, with some spinning several hundred times per second. This rapid rotation, combined with their powerful magnetic fields, creates pulsars, the neutron stars that emit beams of radiation. These beams of radiation sweep across the cosmos, and when they align with Earth, we detect them as regular pulses. These pulsars offer researchers a unique opportunity to study the fundamental forces of the universe. Neutron stars serve as cosmic laboratories for extreme physics, providing a natural environment in which to test theories of gravity and matter. Observing the behavior of matter in such intense gravitational fields can shed light on the limits of our understanding of physics, including the nature of spacetime itself. Additionally, the study of neutron stars offers a glimpse into the exotic states of matter that may exist under such extreme conditions, potentially challenging and expanding our current theories. Neutron stars, with their immense gravitational forces and unique properties, serve as some of the universe's most powerful clues in our quest to understand its deepest mysteries. These incredibly dense remnants of massive stars push the boundaries of physics, revealing information about the most fundamental forces that govern the cosmos. When two neutron stars collide, the event is nothing short of catastrophic, a cataclysmic spectacle that unleashes a massive burst of energy in the form of gravitational waves. Along with this cosmic shockwave, heavy elements such as gold and platinum are scattered across the universe. This cosmic synthesis is no mere spectacle. It offers profound insight into the origins of these elements and the nature of gravity itself. Far from being just objects of scientific curiosity, neutron stars are essential players in our understanding of the universe, helping us unlock the mysteries of the forces that shape all matter. Black holes, on the other hand, are some of the most enigmatic and captivating objects that exist in the cosmos. They form from the remnants of massive stars once they have exhausted their nuclear fuel. At the end of a star's life, the core undergoes a dramatic collapse, imploding under the weight of its own gravity, while the outer layers often explode in a brilliant supernova. If the remaining mass of the core is sufficient, typically more than 3 times that of the Sun, the core is compressed to such an extent that it forms a singularity, a point of infinite density. Surrounding this singularity is the event horizon, a boundary beyond which nothing, not even light, can escape. The defining characteristics of black holes are their mass, spin, and electric charge. The mass of a black hole determines the strength of its gravitational pull, and black holes can range in size from a few times the mass of the Sun to supermassive black holes containing millions or even billions of solar masses, typically located at the centers of galaxies. The spin of a black hole describes how fast it is rotating, and this rotation can have a profound effect on the space around it. It can, for example, create accretion disks, vast spirals of gas and dust that heat up and emit tremendous energy as they are drawn toward the black hole's event horizon. Perhaps the most intriguing feature of black holes is their event horizon. While not a physical surface in the traditional sense, the event horizon marks the point of no return for anything that crosses it. To an outside observer, an object approaching a black hole seems to slow down as it nears the event horizon, an effect caused by the extreme gravitational time dilation predicted by general relativity. In fact, the object never appears to fully cross the event horizon. Instead, it seems to fade away, frozen in time, at the boundary. Despite their mysterious and seemingly simple nature, black holes offer profound insights into the laws of physics, especially within the realms of gravity and quantum mechanics. As we continue to explore these cosmic giants, we peel back layer upon layer of secrets, raising fundamental questions about the very fabric of reality itself. Their deceptive simplicity belies the complexity and profundity of the mysteries they hold. Galaxies, those vast collections of stars, gas, dust, and dark matter, are the sprawling structures that define much of the cosmos. They come in a variety of shapes and sizes, and they can be classified into three primary types: spiral, elliptical, and irregular. Each type reveals distinct characteristics that contribute to our understanding of the universe's evolution and formation. Spiral galaxies are perhaps the most iconic, featuring a rotating, flat disk filled with stars, gas, and dust. At the center of this disk lies a dense bulge of stars, while elegant winding arms spiral outwards, creating a striking visual display. Our very own Milky Way is a prime example of a spiral galaxy, demonstrating how these systems can continue to form new stars in their arms over time. In contrast, elliptical galaxies are more rounded and lack the distinct structured arms seen in spiral galaxies. These galaxies vary in shape, ranging from nearly spherical to elongated, and consist primarily of older stars. There is little to no ongoing star formation in elliptical galaxies, as the gas and dust necessary for creating new stars have long been exhausted. The formation of elliptical galaxies is often associated with the merging of smaller galaxies, which leads to a more homogeneous population of stars. Irregular galaxies, as the name suggests, do not conform to the structure of either spiral or elliptical galaxies. They appear chaotic, lacking the symmetry and organization of the other types. However, these galaxies are typically rich in gas and dust, providing the necessary ingredients for vigorous star formation. Irregular galaxies often form as a result of gravitational interactions or collisions with other galaxies, making them fascinating examples of the dynamic, ever-evolving nature of the cosmos. Each type of galaxy contributes a chapter to the grand narrative of the universe, illustrating the diverse processes that have shaped the cosmos over billions of years. Once thought of simply as a vast collection of stars, gas, and dust, the Milky Way galaxy reveals itself to be far more complex. Recent discoveries have shown that the Milky Way has a barred spiral structure, reshaping our understanding of its nature. This barred structure suggests that our galaxy is not static, but instead it is a dynamic, evolving system. The identification of a bar in the center of our galaxy has become a critical piece of the puzzle in understanding the formation and evolution of galaxies. Barred spiral galaxies, like the Milky Way, represent a significant phase in the life cycle of many galaxies. The presence of the bar channels gas towards the center of the galaxy, leading to intense star formation as material accumulates. This realization provides a clearer picture of how galaxies evolve and how their structural features can directly influence the processes that occur within them. By studying the structure of the Milky Way and other barred galaxies, astronomers can better understand the relationship between a galaxy's form and its energetic developmental processes. This interconnectedness between structure and function underscores the ever-evolving, intricate nature of our universe. Galaxies, vast cosmic structures composed of stars, gas, dust, and dark matter, are far from solitary travelers in the universe. Instead, they engage in a dynamic and intricate cosmic dance, influenced by the gravitational forces exerted by one another. When galaxies draw near, their mutual gravity can spark a wide range of interactions, some subtle and peaceful, others dramatic and transformative. As researchers delve deeper into understanding these interactions, they are discovering that these cosmic encounters are pivotal in shaping the evolution of galaxies over time. This newly gained insight also prompts a fresh perspective on the Milky Way. Traditionally regarded as a barred spiral galaxy, The Milky Way's structure is not just a feature of aesthetic beauty, but a crucial factor in how it interacts with neighboring galaxies. The unique barred spiral configuration of the Milky Way suggests that it may have a significant influence on its gravitational interactions with nearby galaxies. Such structural traits may play a key role in shaping the evolution of the galaxy, influencing how it forms bonds, shares matter, and even collides with others across vast cosmic distances. As astronomers apply this understanding to other galaxies with similar structures, they can make more accurate predictions about how these galaxies will evolve based on their specific physical characteristics. This deeper understanding of the Milky Way's structure leads us to ask larger questions about the universe itself. If the shape of a galaxy influences its gravitational interactions, could this dynamic process play a part in the formation of galaxies across the cosmos? By exploring the Milky Way in greater detail, astronomers are not only shedding light on our own galaxy's history, but they are also uncovering vital information about the life cycles of countless other galaxies throughout the universe. This, in turn, provides a more complete picture of the cosmic tapestry that connects all galaxies. In the grand scheme of the cosmos, galaxies do not exist in isolation. Their vast structures and dynamic behaviors are constantly in flux, molded by the gravitational forces they exert on each other. Galaxies often come into close contact with one another, and their mutual gravity can lead to fascinating encounters that are far from ordinary. These interactions might be peaceful, manifesting as subtle changes, or they may trigger dramatic transformations that reshape entire galaxies. One of the most striking outcomes of such interactions is the process known as galactic mergers. When two galaxies collide, they can merge into a single, more massive galaxy. This dramatic event can take millions or even billions of years, but the results are nothing short of spectacular. As gas clouds within the colliding galaxies compress and heat up, new stars are born, illuminating the galactic night sky in a brilliant display. These mergers can also give rise to galaxies with irregular shapes, telling the story of the cosmic forces at play. However, not all galactic encounters lead to mergers. In some cases, galaxies pass by one another at great speeds, their gravitational forces pulling and stretching their gas and stars apart. This tidal interaction can give rise to striking new structures, such as tidal tails or streams of stars that stretch out from the galaxies. These elongated forms are a testament to the delicate balance of forces at work during such encounters, painting a vivid picture of the interaction's impact on the galaxies involved. In the densest regions of the universe, particularly at the centers of galaxy clusters, more complex interactions take place. Here, galaxies can collide repeatedly, leading to even higher rates of star formation. As material is stripped away from the colliding galaxies, it can fuel these bursts of star birth, further altering the galaxy's structures. Each such encounter leaves a lasting mark on the galaxies, shaping not only their individual histories but also the broader landscape of the universe. Through these cosmic interactions, galaxies tell the story of the universe's evolution, revealing just how interconnected and dynamic the cosmos truly is. At the heart of many of these galaxies lies a powerful and enigmatic force, the supermassive black hole. These massive objects, which can have a mass millions or even billions of times that of the Sun, exert an immense gravitational pull on their surroundings. Nearly every large galaxy is thought to host one of these behemoths at its center, and understanding their role is key to unraveling the mysteries of galaxy formation and evolution. Supermassive black holes do more than just anchor their galaxies. They profoundly affect the motion of stars and gas within their host galaxy. As objects move in the intense gravitational field near a black hole, their speeds and trajectories become highly influenced, as though the galaxy is bound to the rhythm of an invisible cosmic clock. This enables astronomers to map the distribution of both visible and dark matter within the galaxy. Observations have shown that the presence of a supermassive black hole can even alter the orbits of stars that venture too close, pushing them into increasingly erratic paths as they spiral inward. Around these black holes lies an accretion disk, a vast swirling mass of gas and dust drawn in by the black hole's gravity. As this material spirals inward, friction and gravitational forces heat it to extreme temperatures, often producing intense radiation, including X-rays. This energetic activity isn't confined to the black hole itself. It can create powerful jets of particles that shoot out from the poles of the black hole, influencing the interstellar medium and potentially triggering star formation in the surrounding galaxy. Thus, supermassive black holes play a central role in the dynamics of galaxies. Their gravitational influence shapes the structure of their host galaxies, while their energetic emissions can influence the birth and death of stars. They are not just dark and mysterious objects. They are key players in the delicate dance of attraction, energy, and matter that defines the evolution of galaxies. Through these cosmic phenomena, galaxies are telling the story of the universe's evolution. Each interaction, whether peaceful or catastrophic, adds a chapter to the grand narrative of cosmic history. As astronomers continue to explore these fascinating processes, they are painting a richer, more detailed picture of the universe we inhabit, one that is far more interconnected and dynamic than we could have ever imagined. The life cycles of galaxies, shaped by gravitational forces, star births, and black hole activity, ultimately contribute to the complex and ever-evolving tapestry that defines the cosmos. Galaxy clusters are foundational to our comprehension of the universe's large-scale structure. These immense formations consist of galaxies, gas, and dark matter, bound together by gravity. They can hold hundreds, even thousands, of galaxies and span vast regions stretching across millions of light years. The enormous size and mass of these clusters make them essential players in the cosmic web, offering critical insights into the evolution of galaxies and large-scale structures over billions of years. When astronomers study galaxy clusters, they can map the distribution of matter across the universe. The way these clusters form and evolve is shaped not only by visible matter, like stars and gas, but also by invisible components, such as dark matter. Observing the clustering of galaxies offers scientists the opportunity to infer the presence of dark matter, which constitutes about 25% of the universe's total energy density. The arrangement and movements within galaxy clusters further shed light on the geometry of the universe and its expansion, helping to unlock the mystery of dark energy, which makes up roughly 70% of the universe. Galaxy clusters also serve as natural laboratories for studying cosmic processes. The hot gas that fills the space between galaxies emits X-rays, which can be detected by space telescopes. This provides astronomers with vital information about temperature and density, offering clues about how these clusters form and the forces that govern them. The merging of galaxy clusters can create shock waves and other cosmic phenomena, which reveal how matter and energy behave under extreme conditions. These observations offer essential insights into the fundamental nature of the universe itself. But galaxy clusters are not merely a collection of galaxies. They are central to unraveling the profound mysteries of the cosmos. By studying their formation, distribution, and evolution, scientists can construct a clearer picture of the universe's composition and history. Ongoing research into these colossal structures enhances our understanding of the forces that have shaped the universe across time. Every discovery we make adds another layer to our comprehension of the cosmic forces at play. Similarly, the discovery of exoplanets, planets that exist outside our solar system, has dramatically reshaped our understanding of the universe. The search for these distant worlds has been propelled by a range of innovative techniques, each uncovering new dimensions of the cosmos. One of the most widely used methods is the transit technique. Here, astronomers monitor the brightness of a star and look for periodic dips, which occur when an exoplanet passes directly in front of the star, blocking a fraction of its light. This method has proven invaluable and was extensively employed by the Kepler Space Telescope, expanding our knowledge of planetary systems far beyond our own. Another crucial method is the radial velocity technique, which involves measuring the subtle wobbles of a star caused by the gravitational influence of an orbiting planet. As the planet moves, it causes a small but detectable movement in the star itself. By analyzing shifts in the star's light spectrum, scientists can confirm the presence of a planet, determine its mass, and calculate its orbit. This technique has played a vital role in validating many exoplanet discoveries first detected through transits. The diversity of exoplanet types that have been uncovered is nothing short of astounding. Among the most surprising findings are the hot Jupiters, large gas giants that orbit extremely close to their stars. These planets defy our previous assumptions about how planetary systems should form. Moreover, the discovery of Earth-sized exoplanets within the habitable zone, the region around a star where conditions could be just right for liquid water, has ignited excitement about the potential for alien life. Estimates suggest there may be billions of Earth-like planets scattered throughout our galaxy alone, and each discovery challenges our preconceived notions, broadening our understanding of planetary formation and the possibilities for life beyond Earth. As technology advances and our observational capabilities improve, the quest to understand the universe's exoplanetary landscape continues. Each new discovery provides further clues about the cosmos and our place within it. This ongoing exploration is a reminder of how much we have yet to learn about the universe. When we turn our attention to the search for potentially habitable exoplanets, one captivating aspect takes center stage: the hunt for planets that might support life. These distant worlds, which orbit stars beyond our solar system, possess certain key characteristics that make them prime candidates for habitability. First, they must lie within a star's habitable zone, the so-called Goldilocks zone, the region where conditions are neither too hot nor too cold for liquid water to exist on a planet's surface. In addition to being in the right location, potentially habitable exoplanets tend to be similar in size to Earth. Scientists hypothesize that planets larger than Mars but smaller than gas giants like Neptune are more likely to have the right conditions for supporting life. The size of the planet plays a key role in retaining an atmosphere, which in turn regulates temperature and shields the surface from harmful radiation. The composition of the atmosphere is equally important. It should contain gases such as oxygen and carbon dioxide, which are essential for life as we know it. To assess the viability of these planets for supporting life, astronomers use various methods. One such technique involves analyzing the starlight that passes through a planet's atmosphere during a transit. This can reveal the chemical makeup of the atmosphere, offering insights into whether the necessary elements for life are present. In addition to atmospheric analysis, the study of a planet's surface temperature and geological features provides critical information about its environment. Techniques such as spectroscopy allow scientists to observe a planet's surface in unprecedented detail, offering clues about whether it could host life forms. As we continue to refine our methods and expand our reach into the cosmos, we edge closer to answering one of the most profound questions of all: are we truly alone in the universe? The search for habitable exoplanets is far more than a scientific endeavor. It is a deeply philosophical pursuit that challenges our understanding of life, the universe, and our place within it. Each new discovery brings us closer to an answer, but also reminds us of the vastness of the cosmos and the infinite possibilities it holds. Through the exploration of exoplanets and galaxy clusters, we deepen our understanding of the universe and the forces that govern it, pushing the boundaries of human knowledge to places we could once only dream of. The field of astrobiology has emerged as a groundbreaking interdisciplinary domain that brings together knowledge from a range of scientific fields, including molecular biology, geology, and planetary science. Its aim is to enrich our understanding of what constitutes a habitable environment. As new telescopes and cutting-edge instruments continue to evolve, the search for potentially habitable exoplanets is expanding at an unprecedented rate. Every new discovery holds the power to challenge and potentially reshape our existing understanding of life in the universe. These discoveries serve as a profound reminder that we are part of a vast, enigmatic cosmos filled with untapped mysteries and boundless possibilities. A central focus of astrobiology lies in the search for biosignatures, indicators that could reveal the presence of life beyond Earth. A biosignature is any substance or phenomenon that provides scientific evidence of past or present life. These may include gases such as oxygen and methane, which on Earth are predominantly produced through biological processes. When scientists analyze the atmospheres of distant exoplanets, they actively search for these compounds as potential indicators of life, or at least signs of life that may have existed at some point in the planet's history. Detecting biosignatures is a highly intricate process requiring the use of advanced techniques and state-of-the-art instruments. For example, telescopes equipped with sophisticated spectrometers can analyze the light emitted or absorbed by distant planets and their atmospheres. By studying how this light interacts with the atmosphere, scientists can identify the chemical makeup of the planet's environment. If the atmosphere is rich in oxygen and methane, it raises compelling questions. Could there be life forms similar to those on Earth actively producing these gases? This quest for signs of life is not confined to faraway exoplanets. Exploration within our own solar system is equally vital in the search for extraterrestrial life. Rovers sent to Mars are tasked with seeking out organic compounds and signs of liquid water, while spacecraft sent to the icy moons of Jupiter and Saturn, such as Europa and Enceladus, are probing subsurface oceans that might harbor microbial life. Each new discovery in these locations brings us closer to answering the profound question of where life might exist in the universe. These missions explore entirely new territories, pushing the boundaries of our knowledge and offering tantalizing glimpses of what might lie beyond our own planet. Ultimately, the study of biosignatures is helping to redefine our conception of life itself. It encourages us to think beyond Earth-based biology and imagine the wide array of forms life might take. As we continue to refine our technologies and expand our understanding, each new discovery brings us one step closer to answering the timeless question, are we alone in the universe? This pursuit not only fuels scientific curiosity, but also stirs the human imagination, invoking the possibilities of life in the farthest reaches of space. Our search for extraterrestrial life is not just a scientific endeavor, but also a reflection of the resilience of life on Earth. Earth is home to some of the most extreme environments imaginable, and the organisms that thrive in these conditions offer valuable insights into the potential for life elsewhere. Take, for instance, the hot springs of Yellowstone National Park. These boiling, acidic pools are home to extremophiles, organisms that thrive in what would be considered inhospitable conditions by most other life forms. The heat and acidity of these springs mimic conditions on other celestial bodies, such as the subsurface of Europa, one of Jupiter's moons. Studying these organisms allows scientists to consider the possibility that life could exist in similarly harsh environments on distant worlds. The deep-sea hydrothermal vents along mid-ocean ridges present another example of life's remarkable adaptability. These vents, where water spews out from beneath the Earth's crust, heated by volcanic activity, host entire ecosystems that rely not on sunlight but on chemosynthesis. Entire communities of organisms, such as tube worms and giant clams, survive in total darkness, driven by chemical reactions rather than solar energy. This discovery reshapes our understanding of where life can exist, suggesting that life could thrive in dark, nutrient-rich environments far from any source of light, such as the ocean floors of distant planets. Even in the most frigid environments, life has found a way to endure. In Antarctica, certain microorganisms have evolved to survive extreme cold and intense ultraviolet radiation. These tiny life forms enter a dormant state, able to withstand temperatures far below freezing for extended periods. This resilience strengthens the notion that life could potentially survive in similarly harsh, cold environments like the moons of Saturn and Jupiter, such as Titan, where conditions are equally cold and hostile. Another fascinating example of life's resilience can be found in the Atacama Desert in Chile, one of the driest places on Earth. Here, microbial life persists in arid conditions, surviving on the limited rainfall and moisture that occasionally replenishes the land. Microorganisms have been discovered deep within the salt flats, showcasing their remarkable adaptations to extreme drought. This discovery raises intriguing questions about how life might survive on planets or moons with similarly limited water resources. The existence of such extreme habitats on Earth underscores the importance of exploring and understanding these environments, both here and on distant worlds, to better comprehend where life could take root in the universe. Each of these extreme habitats offers a unique window into the versatility of life, reminding us that life could exist in forms and environments beyond our wildest imaginings. As we search for life beyond our planet, these environments teach us the value of persistence, adaptation, and survival. traits that could define life on other worlds as well. Water remains a central element in the search for extraterrestrial life, serving as a vital solvent that facilitates the chemical reactions necessary for life. On Earth, life relies on water's unique properties, including its ability to dissolve nutrients and support metabolic processes. Because of its central role in biological systems, the presence of water is often considered one of the key indicators in the search for life beyond Earth. In our own solar system, bodies such as Mars, Europa, and Enceladus have provided compelling evidence of water, either in liquid form or as ice. Mars, for example, has revealed signs of ancient water flow, and researchers have even discovered the presence of salty liquid brines beneath the planet's surface. Europa, one of Jupiter's moons, is especially intriguing due to the existence of a subsurface ocean beneath its icy crust. If hydrothermal vents are present on the ocean floor, they could provide the perfect conditions for life to thrive, similar to those found in Earth's deep-sea ecosystems. Additionally, scientists speculate that life could survive even if water exists not in liquid form, but as ice or vapor. The versatility of water in supporting life increases the potential locations where life could emerge or persist in some form. The presence of water, whether as liquid, ice, or vapor, broadens the possibilities for discovering extraterrestrial life. Scientists are currently studying transient water vapor in the atmospheres of distant exoplanets, attempting to identify the conditions that could support life. The search for water is inextricably linked to the search for life, as water's fundamental role in biological processes makes it a crucial ingredient in the existence of life as we know it. As we continue to explore the cosmos, the discovery of water, whether on Earth, on distant planets, or in the moons of our solar system, opens up a host of exciting possibilities. The presence of water not only increases the likelihood of finding life, but also provides a reminder that the conditions necessary for life may exist in countless corners of the universe, far beyond our current reach. In addition to the search for life and water, our understanding of the universe has been profoundly enriched by the discovery of gravitational waves. These ripples in the fabric of spacetime are produced by some of the most violent and energetic processes in the universe. Much like the ripples that spread out when a pebble is dropped into a calm pond, gravitational waves propagate across the cosmos when massive objects, such as black holes or neutron stars, collide or accelerate. These waves travel through spacetime and can be detected by highly sensitive instruments. In September of 2015, a monumental achievement in physics and cosmology occurred when scientists at the LIGO Observatory recorded the first direct observation of gravitational waves. This landmark event marked the beginning of a new era in astronomy, offering a new way to study the universe. For centuries, our exploration of space was limited to observing light, whether visible, ultraviolet, or X-rays. The detection of gravitational waves, however, opened an entirely new window into the cosmos, allowing us to perceive cosmic events that were previously undetectable. The implications of this discovery are profound. Not only does it confirm a major prediction of Albert Einstein's theory of general relativity, but it also enhances our understanding of phenomena such as black holes, neutron stars, and the aftermath of the Big Bang. Each detection of gravitational waves offers a unique fingerprint, providing insights into the dynamics of the universe and the processes that have shaped its evolution. Gravitational wave astronomy is experiencing a rapid transformation, fueled by the growing number of observatories coming online across the globe. As these facilities begin to function at full capacity, the floodgates to a new era of cosmic discovery are opening wide. We are standing at the precipice of a revolution in how we understand the universe, one that could reshape our entire understanding of cosmic history and its most elusive phenomena. In a sense, humanity is just beginning to tune in to the grand symphony of the cosmos, with gravitational waves acting as the novel cosmic language that will help us decode its most profound mysteries. These waves, ripples in the fabric of space-time itself, are the echoes of some of the universe's most energetic and cataclysmic events. With each detection, we uncover new information about the dynamic, ever-evolving universe that we live in, events so subtle yet powerful that they could forever alter the trajectory of astrophysical research. The growing field of gravitational wave astronomy invites us to listen in ways we never imagined, offering us insights into phenomena that were once beyond our reach. One of the most profound phenomena that continues to challenge our understanding of the universe are gamma-ray bursts. These explosive events are some of the most energetic and mysterious occurrences in the cosmos, capable of releasing more energy in a few seconds than the sun will emit in its entire lifespan. Their origin, usually traced back to distant galaxies, is a cosmic enigma. When these bursts occur, they can outshine entire galaxies, overwhelming everything else in their vicinity with their intense brightness. The staggering power and radiant energy of gamma-ray bursts have forced scientists to reassess their theories about how energy is produced on a cosmic scale, sparking new investigations into the extreme processes that give rise to such colossal bursts of energy. Yet, the true complexity of gamma-ray bursts lies in their unpredictability. For decades, astronomers could detect these powerful flashes without any clear understanding of their source. Some were linked to the collapse of massive stars, resulting in supernova explosions, while others seemed connected to the merging of neutron stars. This diverse set of potential origins points to the likelihood that there are multiple processes at work, each contributing to these bursts in unique and yet-to-be-understood ways. Unraveling the connections between these scenarios remains one of the most compelling puzzles in modern astrophysics. Moreover, gamma-ray bursts provide an unprecedented window into the evolution of the universe itself. These distant cosmic beacons illuminate the vast distances between galaxies and offer a glimpse into the ages of stars and galaxies that are home to these bursts. Studying these events has opened new avenues for understanding the conditions that prevailed in the early universe, offering clues about star formation and galactic evolution. With each new discovery, our understanding of the life cycles of stars and the processes that govern the cosmos expands, forcing us to constantly redefine our perceptions of what is possible in the universe. Each observation of these extraordinary events sparks deeper questions and invites us to peer further into the mysteries of the cosmos, a reminder that while the universe is vast and complex, it still holds countless secrets waiting to be uncovered. Pulsars, fascinating celestial objects that can be likened to the universe's most precise clocks, also play a critical role in our understanding of the cosmos. These rapidly rotating neutron stars are the remnants of supernova explosions, emitting regular pulses of radiation from their magnetic poles. As they spin, the beams of radiation sweep through space. If one of these beams intersects Earth's line of sight, we detect a pulse of radiation. This regular pulsing phenomenon allows astronomers to study the stars in an entirely new way, with the remarkable consistency of the pulses making them vital tools for studying both stellar evolution and the extreme environments found in the universe. But the importance of pulsars stretches far beyond their mesmerizing flickering lights. They offer crucial insights into the fundamental laws of physics, particularly in the realm of gravitational theory. By observing the timing of pulsar signals, scientists can detect gravitational waves, ripples in spacetime generated by massive events such as black hole mergers. By analyzing variations in the pulse timing, researchers can even map the gravitational landscape around these catastrophic cosmic events, deepening our understanding of how massive objects interact within the vastness of the universe. Pulsars also contribute significantly to our knowledge of the structure and content of our own galaxy. By tracking their positions and movements, astronomers gain insight into the distribution of dark matter and the gravitational forces at work within the Milky Way. This information is essential for understanding galaxy formation and dynamics, revealing how galaxies evolve over time and the invisible forces that shape them. But the potential applications of pulsars don't stop there. Their predictable signals are being explored as a potential navigation system for deep space exploration, acting as a cosmic GPS to guide spacecraft across the vast reaches of the universe. Pulsars are not merely objects of scientific fascination. They are essential tools in our quest to explore the cosmos, unlocking more of its secrets with every discovery. Similarly, quasars, some of the brightest and most energetic objects in the universe, are revealing astonishing truths about the cosmos. Powered by supermassive black holes at the centers of distant galaxies, quasars emit beams of light across the electromagnetic spectrum, including radio, optical, and X-rays. This intense luminosity allows them to be visible from billions of light years away, making them among the most distant objects we can observe. When we look at quasars, we are not just seeing distant points of light. We are peering back in time, viewing these objects as they existed billions of years ago, in the early stages of the universe. This makes quasars a unique tool for studying the conditions of the universe in its infancy, particularly in the few billion years following the Big Bang. By examining the light emitted by quasars, astronomers gain invaluable information about the formation and evolution of galaxies, the distribution of gas and dust in the cosmos, and the relationship between black holes and their host galaxies. Furthermore, the light from quasars passes through the intergalactic medium, interacting with the gas and dust between galaxies. These interactions leave distinct imprints on the light, which scientists can analyze to learn about the composition and density of matter in the universe at different points in its history. In this way, quasars not only shed light on the evolution of galaxies, but also help probe the vast, unseen components of the cosmos. Finally, dark energy, one of the most enigmatic forces in the universe, plays a pivotal role in the ongoing expansion of the cosmos. Observations in the late 20th century revealed a shocking discovery. The universe is not just expanding, it is accelerating. This observation forced scientists to propose dark energy as the driving force behind this mysterious acceleration. If we imagine the universe as a balloon being inflated, dark energy functions like an ever-increasing air pump, causing the balloon to expand more rapidly with each passing moment. This cosmic inflation is pulling galaxies apart at an accelerating rate, pushing the universe further into an uncertain future. The implications of dark energy are vast and far-reaching. It suggests that the universe will continue to expand indefinitely, and with that expansion comes the potential for a future where galaxies, stars, and even black holes drift beyond our observable horizon. Some scientists believe this may lead to a scenario known as the Big Freeze, where galaxies become so distant from one another that they vanish from our view, leaving behind a cold, dark universe. As dark energy continues to influence the fate of the cosmos, its full nature remains one of the most tantalizing mysteries in modern astrophysics. Each new discovery about dark energy pushes the boundaries of our knowledge, urging us to rethink our understanding of the universe's future and its ultimate destiny. Moreover, dark energy raises some of the most profound and perplexing questions about the fundamental nature of reality. What exactly is this enigmatic force that seems to dominate the vast majority of the cosmos? Does it exist merely as a cosmological constant, or could there be more to it than we currently understand? As scientists delve deeper into the mysteries of dark energy, they find themselves constantly rethinking aspects of physics that were once considered settled. This elusive force challenges our comprehension of space, time, and even the fundamental structure of the universe itself. The pursuit of understanding dark energy remains one of the most thrilling and intellectually demanding endeavors in modern astrophysics. The theory of relativity, developed by Albert Einstein in the early 20th century, revolutionized our understanding of time, space, and gravity. It fundamentally altered long-held beliefs that had stood for centuries. Before Einstein, scientists viewed space as an unchanging, infinite backdrop against which all events unfolded, and time as a constant linear progression that ticked away the same for everyone, everywhere. But Einstein's genius introduced a groundbreaking new perspective. Space and time are not separate, static entities. Rather, they are intertwined in a dynamic, flexible fabric that can warp and bend depending on the motion of observers and the influence of gravity. At the heart of Einstein's theory lies the concept that time is not absolute. It is malleable. Time is no longer a rigid, unyielding flow. Instead, it stretches and contracts depending on how fast you are moving and the strength of gravitational fields around you. This is known as time dilation. For example, if you were to travel at speeds close to the speed of light, you would experience time more slowly than someone who remained on Earth. This phenomenon sounds like something out of science fiction, but It has been confirmed through experimental evidence, such as precise measurements made using atomic clocks. Space, too, is not the immutable void it once seemed to be. Einstein's general theory of relativity shows that mass and energy warp the fabric of space-time itself. The more massive an object, like a planet or a star, the greater its effect on space-time. In turn, this curvature affects everything around it, from the paths that light travels to the passage of time itself. The very fabric of the universe is dynamic, not static, and mass and energy shape it in ways that challenge our intuitive understanding of reality. The implications of these ideas are vast and profound. They force us to confront the idea that the universe is far more interconnected and fluid than we ever imagined. Reality itself, it seems, is far more flexible than our senses can grasp. Einstein's theory of relativity opened up new ways of exploring the cosmos and pushed us to rethink the very nature of existence. It invites us to examine the universe with fresh eyes, reminding us that our understanding is far from complete. One of the most intriguing consequences of Einstein's theory is the phenomenon of time dilation. Time dilation refers to the difference in the passage of time as observed from different reference frames, especially when objects are moving at different velocities or experiencing varying degrees of gravitational pull. There are two primary ways in which this phenomenon manifests: through relative velocity and the influence of gravity. A classic example of time dilation is the twin paradox. In this thought experiment, two identical twins are born at the same time. One twin stays on Earth, while the other embarks on a journey through space at a significant fraction of the speed of light. When the traveling twin returns, they discover that far less time has passed for them than for their Earth-bound twin. This discrepancy arises because, at high speeds, time for the traveling twin runs slower compared to the twin who remains stationary on Earth. While this might sound like the stuff of science fiction, it has been experimentally verified using high-precision atomic clocks. Time dilation also occurs in the presence of strong gravitational fields. The closer an object is to a massive body like Earth, the slower time will pass for it compared to an object further away from the source of gravity. This effect has been confirmed by placing highly accurate atomic clocks at different altitudes. Clocks located at higher elevations, where the gravitational pull is weaker, tick slightly faster than those at lower elevations, where gravity is stronger. These observations confirm that gravity indeed affects the flow of time itself. Interestingly, time dilation isn't just a theoretical concept. It has real-world applications, particularly in technology. The Global Positioning System, GPS, for instance, relies on the precise measurement of time to pinpoint locations. Satellites orbiting the Earth experience time dilation in two ways. Their speed causes their onboard clocks to tick more slowly, and their distance from Earth means they experience a weaker gravitational pull. Engineers must account for these subtle differences in time in order to provide accurate GPS data. What seems like an abstract scientific principle is, in fact, woven into the fabric of our daily lives. Space-time, in Einstein's view, is a four-dimensional continuum that blends three dimensions of space with the dimension of time. You can think of it as a fabric that stretches and bends in response to the presence of mass. In this view, events don't simply occur at a particular place. They occur at a specific time and in a specific relationship to the curvature of space-time at that moment. This idea fundamentally alters our understanding of motion and gravity. In the space-time framework, gravity is not a force pulling objects together, as we once thought. Instead, gravity arises from the curvature of this four-dimensional fabric. When a massive object like a planet or a star distorts space-time around it, other objects nearby move along the curved paths created by this distortion. This means that what we perceive as the force of gravity is, in fact, the result of how space-time itself bends and shapes the motion of objects. Einstein's general theory of relativity provides the mathematical foundation for this understanding, fundamentally changing the way we see the universe. The consequences of this view are profound. It explains why planets orbit stars, why light bends around massive objects, and why even the passage of time is affected by gravity. It also provides a holistic framework for understanding the universe. Everything, from the smallest particles to the largest galaxies, moves and interacts within the vast, interconnected web of space-time. This understanding reinforces the idea that the cosmos is not a collection of isolated objects, but a dynamic, interwoven existence where space and time are inextricably linked. Wormholes, often described as cosmic tunnels or shortcuts through space and time, have long captured the imagination of scientists and science fiction enthusiasts alike. Imagine a bridge that connects two distant points in the universe, allowing for near instantaneous travel between them. These hypothetical shortcuts could potentially bypass the immense distances that separate objects in space, offering a way to traverse the cosmos in ways that defy our traditional understanding of distance and time. The concept of wormholes stems from Einstein's general theory of relativity. According to this theory, massive objects warp space-time in ways that create curvatures or dents in the fabric of the universe. Some solutions to Einstein's equations suggest that these curvatures could take the form of tunnels connecting two separate regions of space-time. Although wormholes remain purely theoretical, the mathematical framework supporting their existence has prompted many researchers to explore the possibility that they could be real. If wormholes could be stabilized and controlled, they might revolutionize space travel. They could potentially allow humanity to reach distant galaxies in mere moments, rather than the millions of years it would take using conventional propulsion methods. Moreover, the possibility of wormholes raises intriguing questions about time travel. Could one traverse not just space, but time itself? Could wormholes enable travel to the past or future, opening up new frontiers in our understanding of the universe? These ideas, while speculative, highlight the incredible potential of Einstein's theory of relativity and our ongoing search for answers about the fundamental nature of reality. They remind us that there is still so much to learn about the cosmos, and the possibilities for discovery are as vast and mysterious as the universe itself. However, while the theoretical foundation behind the concept of wormholes is undeniably compelling, the practical challenges of creating or even discovering a traversable wormhole are staggering. Current scientific understanding indicates that exotic matter, substances with negative energy density, would be required to keep a wormhole open and stable. Unfortunately, these materials remain purely hypothetical, with no experimental evidence to support their existence. As a result, there remain countless unanswered questions surrounding the viability of wormholes. While they undeniably capture the imagination and inspire awe, wormholes also serve as a reminder of the vast mysteries that still lie hidden within the universe, waiting to be unraveled. At the core of understanding the true nature of the cosmos is grasping the concept of the curvature of space-time. This fundamental idea, first introduced through Albert Einstein's theory of general relativity, explains how mass can warp the very fabric of the universe. This curvature is not just a theoretical concept, but a measurable phenomenon. Scientists have developed two powerful methods to observe and study it: gravitational lensing and the precise tracking of planetary motion. Gravitational lensing occurs when a massive object, like a galaxy or even a cluster of galaxies, lies between Earth and a more distant light source, such as a quasar. The immense gravitational field of this intervening mass bends the light from the background object, distorting its appearance. This bending of light can create multiple images or arcs that encircle the massive object. Through careful analysis of these distorted images, astronomers can measure the degree of curvature in space-time, as well as infer details about the mass distribution and the dark matter that may be present in the intervening galaxy. These observations provide valuable insights into the hidden structure of the universe and offer a deeper understanding of its fabric. Another critical approach to studying space-time curvature is through the observation of planetary motion. As planets and other celestial bodies travel through space, their paths can be influenced by the curvature of space-time created by more massive objects. For example, by studying the orbits of planets in our solar system, scientists can use precise measurements of distances and velocities to confirm the predictions made by general relativity. One notable observation is that the orbits of planets are not perfectly elliptical, as originally described by Johannes Kepler. Instead, subtle variations, caused by the curvature of space-time, appear over time. A striking example of this effect can be seen in Mercury, whose orbit gradually shifts, a phenomenon known as orbital precession. This precession was first detected and explained using Einstein's theories, further confirming the validity of general relativity. In addition to these methods, the study of gravitational waves has provided a groundbreaking new way of exploring the curvature of spacetime. Gravitational waves are ripples in the fabric of spacetime created by the violent motion of massive objects, such as when two black holes or neutron stars collide. These waves propagate outward from their source, carrying information about the energy and mass involved in such cataclysmic events. Advanced detectors such as LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo have successfully captured these waves, confirming long-standing predictions about spacetime distortion in extreme conditions. The analysis of gravitational waves has deepened our understanding of how mass and energy interact with spacetime, offering new insights into the nature of the universe and the fundamental forces that govern it. Beyond the immediate structure of our universe, the concept of the multiverse presents an entirely new perspective on reality. The multiverse theory suggests that our universe may not be the only one, but that a vast, possibly infinite number of universes could exist, each with its own distinct set of physical laws and constants. Several interpretations of the multiverse theory exist, each offering a unique vision of how these parallel universes might emerge. One of the most intriguing ideas is the bubble universe theory, which arises from the process of cosmic inflation. During this rapid expansion of the early universe, distinct bubbles of spacetime could have formed, each one representing a separate universe. As these bubbles drift apart, they evolve independently, with their own set of physical properties and laws. This theory envisions a vast landscape of universes, each with its own unique characteristics, giving rise to the idea of a cosmic multiverse. Another prominent interpretation is the many worlds hypothesis, which stems from quantum mechanics. According to this theory, every time a quantum event occurs, the universe branches into multiple outcomes. Each possible outcome takes place in a separate, parallel universe, creating a vast web of alternate realities. In this view, every decision you make could give rise to countless versions of yourself, each living in a universe where you made a different choice. This interpretation radically alters our understanding of reality, suggesting that every action, every possibility, and every outcome plays out across a multitude of universes. Cosmic string theory also contributes to the multiverse concept. According to this theory, the universe is like a giant quilt, with long, one-dimensional cosmic strings acting as the threads that separate different regions of reality. Each region could possess its own fundamental properties, with some areas being habitable, while others remain inhospitable. These cosmic strings might serve as both connectors and boundaries between different universes, illustrating how they might interact with one another while maintaining their individual uniqueness. Finally, the theory of brains, which arises from string theory, posits that our universe is just one three-dimensional brain, short for membrane, existing within a higher dimensional space. Other brains could represent entirely separate universes, occasionally colliding with ours. These collisions could have given rise to events like the Big Bang, marking the birth of our universe. The theory of brains adds a further layer of complexity to the multiverse, suggesting that our universe may not even be the only one within its own higher dimensional space. The diverse interpretations of the multiverse not only stretch the boundaries of our imagination, but also challenge our fundamental understanding of existence. They spark debates across scientific, philosophical, and even spiritual realms, each perspective offering a new lens through which to view the universe. Whether these universes are entirely separate or whether they are interwoven in a vast cosmic web remains to be seen. But the concept of the multiverse has undeniably captured the human imagination. One of the boldest theories to emerge in the realm of fundamental physics is string theory. This framework suggests that the very building blocks of the universe are not point-like particles, as traditionally believed, but tiny vibrating strings. These strings, which can be as small as 10 to the power of -33 centimeters, vibrate at different frequencies, with each frequency corresponding to a different particle. This means that the multitude of particles and forces we observe in nature could all arise from a single fundamental entity: tiny, vibrating strings. String theory also posits that there are more than the familiar three dimensions of space and one of time. In fact, it suggests that there could be as many as 11 dimensions, each with its own unique properties. These additional dimensions could give rise to a variety of possible universes, each governed by its own set of physical laws and constants. This idea not only challenges our current understanding of the universe, but also opens up new possibilities for what might lie beyond the observable world. By incorporating these extra dimensions, string theory suggests that we are part of a vast, interconnected cosmos, with the potential for other universes to exist within the same framework. Whether or not these universes are accessible or even detectable remains an open question. Nevertheless, the concept of a multiverse, as proposed by string theory, invites us to rethink our place in the cosmos and the very nature of reality itself. String theory represents one of the most profound and transformative ideas in the realm of theoretical physics. It not only seeks to explain the fundamental nature of particles and forces, but also introduces a fascinating concept known as the landscape. This landscape is a vast collection of possible solutions to the core equations of the theory. Each solution corresponds to a distinct universe, one with its own set of physical laws. Imagine a reality where gravity operates more strongly or weakly, where time behaves differently than what we experience, or where entirely new laws govern the way things work. The implications of this are staggering, suggesting that the universe we inhabit could be just one of an unimaginable number of others, each with its own unique properties. This notion of a multitude of universes opens up new avenues for understanding the apparent fine-tuning of our own cosmos. Why does our universe seem so perfectly tuned for life? In string theory, the existence of other universes, each with its own specific set of laws, could provide the answer. The multiverse theory, which is intimately tied to string theory, suggests that life exists in our universe not because it is the one and only possibility, but because it happens to be one of the few that can sustain life as we know it. This vision of an infinite cosmic landscape brings us face to face with an idea so vast it feels almost beyond comprehension. Yet, as captivating as this idea is, it presents a series of formidable challenges. The first major hurdle for scientists is that these other universes, if they exist, may be fundamentally different from our own in ways that make them impossible to observe directly. Unlike stars or planets, which we can study through telescopes, these alternate universes might exist in dimensions or forms that are completely inaccessible to our current technology. This lack of direct evidence makes it extraordinarily difficult to gather empirical data, which is essential for validating or refuting any scientific theory. The second major challenge arises from the vast number of potential universes suggested by the multiverse theory. Each universe could have its own distinct set of physical laws, constants, and even fundamental particles. This implies a diversity of realities so immense it becomes nearly impossible to formulate predictions that can be tested with the scientific methods we rely on. If each universe follows a different set of rules, how can we make any measurable predictions about their existence? Without testable hypotheses, the multiverse theory risks devolving into a purely philosophical question about reality rather than a scientifically grounded concept. Moreover, the incorporation of the multiverse into existing frameworks of physics, such as quantum mechanics or cosmology, raises significant questions. While quantum mechanics is renowned for its ability to explain the strange behavior of particles at microscopic scales, it too harbors its own mysteries and paradoxes. These include the concept of superposition, where particles can exist in multiple states at once, and the many worlds interpretation, which suggests that every quantum event results in the creation of a new, parallel universe. But integrating such complex ideas into established scientific theories requires not only creativity, but also careful validation to avoid contradictions with principles that have been rigorously tested and confirmed. And then there is the question of philosophical implications. The very existence of a multiverse challenges the traditional approach to science, which demands that theories be based on observable, repeatable phenomena. If there are universes beyond our reach, existing in realms that cannot be measured, Does this place them beyond the boundaries of science itself? Some argue that anything that cannot be tested falls into the domain of metaphysics, not physics. Can we truly call something science if it lies beyond empirical investigation? The Anthropic principle, which suggests that the universe must be capable of supporting life because we are here to observe it, offers a fascinating perspective when viewed through the lens of the multiverse theory. According to this principle, the conditions necessary for life must exist within our universe simply because life exists to observe them. But when extended to the multiverse, this principle takes on a new dimension. In a vast collection of universes, some may support life, while others may never allow it to emerge. Our universe, with its precisely calibrated physical constants, may simply be one of the few where the delicate balance required for life to thrive happens to occur. This realization leads to deep questions about the nature of reality. Are the laws of physics in our universe simply a coincidence, or do they arise from a much larger framework that allows for a multitude of possibilities? If the multiverse theory holds true, it suggests that the laws of physics that govern our reality may not be unique or special. Instead, we might find ourselves in one of the rare universes where conditions just so happen to support life. This insight holds us, inviting a sense of awe and curiosity about the counterverses that might exist beyond our own. What other kinds of realities might exist? Could there be universes where the fundamental constants of nature are completely different, where life, as we understand it, cannot exist? The exploration of the Anthropic principle and the multiverse raises profound philosophical questions that go far beyond the realm of traditional scientific inquiry. They push us to consider our place in the cosmos, inviting us to reflect on the vastness of reality and the intricate, often mysterious, connections between science and philosophy. This interplay deepens our fascination with both fields, enriching our understanding of the universe and our role within it. At the heart of this discussion is quantum mechanics, the science that deals with the behavior of particles at the atomic and subatomic levels. At first glance, quantum mechanics might seem far removed from the multiverse theory, but in fact, it provides a crucial framework for understanding parallel realities. Quantum mechanics introduces the concept of superposition, where particles exist in multiple states simultaneously until observed or measured. This principle implies that every quantum event might give rise to multiple outcomes, each occurring in its own parallel universe. Imagine a coin toss. In one universe, the coin lands heads up, while in another, it lands tails up. This notion of multiple outcomes occurring simultaneously is central to the idea of the multiverse. Additionally, the many worlds interpretation of quantum mechanics proposes that every quantum event splits the universe into multiple branches, each one representing a different possible outcome. This means that, theoretically, there could be infinite versions of ourselves existing in separate universes, each living out different versions of our lives based on the choices we make or the events that transpire. Quantum mechanics, in this sense, offers a tantalizing glimpse into a reality that stretches far beyond our ordinary understanding. Ultimately, the relationship between quantum mechanics and the multiverse forces us to rethink everything we know about existence. The behavior of the tiniest particles in the universe, which seems so trivial at first glance, may actually offer profound insights into the nature of the cosmos as a whole. As we delve deeper into the mysteries of quantum mechanics, we are reminded of just how interconnected the universe is, and how much we have yet to discover. The possibility that our reality might be only one of countless others invites us to explore the uncharted territories of the multiverse, where the boundaries of space, time, and even existence itself are stretched beyond imagination. The journey into the unknown is far from over, and with each new discovery, we uncover more of the immense and awe-inspiring complexity of the cosmos. The existence of dark matter is one of the most profound mysteries in modern astrophysics. A vast body of astronomical observations supports its presence, revealing its crucial influence on the universe. The evidence comes from various sources, each pointing to a hidden form of mass that cannot be detected by ordinary means, yet exerts a significant gravitational pull. One of the most compelling pieces of evidence comes from the motion of galaxies within galaxy clusters. When scientists observe the way galaxies move and orbit around the center of these clusters, they find that the visible matter, such as stars and gas, does not provide enough gravitational force to explain their observed velocities. Instead, the galaxies are moving too fast for the amount of visible matter present. This discrepancy suggests that there is a substantial amount of unseen mass, what we call dark matter, keeping these galaxies bound together. This unseen mass, although invisible, is essential for holding the structure of galaxy clusters intact, preventing them from flying apart, despite the high speeds at which the galaxies are moving. In addition to this, the structure of the universe on a cosmic scale offers further clues about dark matter. Observations of the cosmic microwave background, CMB, radiation, the faint afterglow of the Big Bang, reveal small fluctuations in temperature that correspond to variations in the density of matter in the early universe. These tiny fluctuations, which were first detected in the 1990s, provide a snapshot of the universe just after its formation. The patterns of these temperature fluctuations match predictions that require a large amount of dark matter. Without it, the formation and clustering of galaxies over billions of years would not be possible. The cosmic structure we observe today, from galaxy superclusters to vast voids between them, is only explainable if a hidden, invisible mass was present in the early universe to guide the formation of these structures. Gravitational lensing, another fascinating phenomenon, offers even more evidence of dark matter's existence. This effect occurs when massive objects, such as clusters of galaxies, bend and distort the light coming from objects behind them. According to Einstein's theory of general relativity, mass curves the fabric of space and time. When astronomers observe light bending in this way, they can infer the mass of the object causing the distortion. What they find is that the mass required to explain the bending is far greater than what can be accounted for by visible matter alone. This discrepancy points directly to dark matter as the hidden source of the additional mass. Gravitational lensing allows astronomers to create maps of dark matter by studying how the light from background galaxies is distorted. The greater the distortion, the more mass is present in the foreground galaxy or cluster, indicating the presence of dark matter. By analyzing thousands of background galaxies and their distorted shapes, scientists can create detailed maps that reveal where dark matter is concentrated in the universe. Even though dark matter cannot be seen directly, these maps allow researchers to trace its distribution across vast cosmic distances. The results have shown that dark matter makes up about 25% of the total mass and energy content of the universe, a staggering proportion that has radically transformed our understanding of the cosmos. These maps not only confirm the existence of dark matter, but also shed light on its critical role in shaping the formation and evolution of galaxies. Dark matter is fundamentally different from ordinary visible matter. While regular matter interacts with all four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, dark matter appears to interact only through gravity. This lack of interaction with light makes dark matter invisible to our current instruments. As a result, dark matter cannot be observed directly, but it reveals itself through its gravitational influence on visible matter. The fact that it interacts so weakly with other forces makes it incredibly elusive, and it is this chasm between dark matter and ordinary matter that presents one of the greatest challenges for scientists. But the universe's mysteries do not end with dark matter. There is another enigmatic force that plays a crucial role in the evolution of the cosmos: dark energy. This force, which is responsible for the accelerated expansion of the universe, makes up about 70% of the total energy content of the cosmos. While gravity pulls matter together, dark energy seems to work in the opposite direction, pushing the universe apart. The discovery of dark energy came as a surprise to astronomers in the late 20th century, when they observed that distant galaxies were moving away from us faster than expected. This observation was puzzling, as it contradicted the prevailing theory that the expansion of the universe was gradually slowing due to the gravitational pull of matter. In response, scientists propose that dark energy acts like a kind of anti-gravity, exerting a repulsive force that overcomes the attractive pull of gravity on large cosmic scales. This repulsive force is responsible for the accelerating expansion of the universe. Unlike matter and energy, which clump together under the influence of gravity, dark energy appears to be evenly distributed throughout space. This uniformity means that no matter where you look in the universe, dark energy's influence remains constant, pushing galaxies and cosmic structures apart as the universe continues to expand. The nature of dark energy is still not fully understood, and its true origin remains one of the most profound questions in cosmology. Some theories suggest that dark energy could be a property of space itself, while others propose that it might arise from new and unknown physics. Despite the uncertainties surrounding its origin, dark energy is central to our understanding of the fate of the universe. As the universe continues to expand, dark energy is the force that will determine its ultimate destiny. Whether the universe will continue expanding indefinitely, slow down, or eventually collapse is still unknown, but dark energy will play a crucial role in shaping that future. Before the discovery of dark energy, scientists believed that the universe's expansion was slowing down due to the gravitational pull of matter. The idea was that the attractive force of gravity would eventually overcome the expansion, leading to a gradual slowdown and possibly a collapse of the universe. This view was based on the observable behavior of celestial bodies, which seemed to be bound together by gravity. However, the discovery of dark energy upended this theory, revealing that the expansion of the universe is actually accelerating. In conclusion, the mysteries of dark matter and dark energy have revolutionized our understanding of the universe. While dark matter remains hidden from direct observation, its gravitational effects are undeniable, shaping the formation and structure of the cosmos. Meanwhile, dark energy has changed our conception of cosmic evolution, showing us that the universe is not only expanding, but accelerating in its expansion. As astronomers continue to probe the depths of the universe, these two enigmatic forces will remain central to our quest for knowledge about the ultimate fate of the cosmos. However, the discovery of dark energy has added a surprising twist to our understanding of the universe. Dark energy is a mysterious force that drives the accelerated expansion of the cosmos, directly challenging the long-held belief that gravity would be the dominant force over vast cosmic distances. The idea of dark energy first gained traction in the late 1990s when astronomers observed distant supernovae that were dimmer than expected. Instead of simply receding from us at a steady pace, these supernovae revealed something startling. The expansion of the universe was not only ongoing, but actually speeding up. This revelation forced scientists to reconsider centuries of established cosmic science. The universe, once thought to be on a slow path toward eventually contracting back on itself due to gravity, now appeared to be on a radically different trajectory. The prevailing thought today is that the universe will continue expanding indefinitely, its boundaries stretching further and further apart. This shift in perspective carries profound implications, not only for the fate of galaxies, but also for the fundamental structure of the cosmos itself. With dark energy accounting for roughly 70% of the universe's total energy content, understanding its nature and behavior is essential. It challenges not only our grasp of gravity, but also the very fabric of spacetime. The mystery of dark energy propels us into a deeper exploration of questions about the origin and future of the universe. As scientists work to uncover its elusive properties, we are confronted with new frontiers in physics. Studying dark energy not only brings us closer to understanding the universe's current state, but it also pushes us to contemplate what lies ahead in the cosmic journey. The quest for knowledge persists, driven by an insatiable curiosity to comprehend the ever-expanding universe. Dark matter and dark energy, two of the most enigmatic phenomena in cosmology, together constitute about 95% of the total content of the universe. Despite their overwhelming presence, these forces remain largely invisible and undetectable. Scientists worldwide are pouring resources into a variety of experiments and observational studies, eager to reveal their hidden nature. The excitement within the scientific community is palpable, as each new discovery promises to unlock a critical piece of the cosmic puzzle. One of the most significant efforts in this pursuit is taking place at large-scale observatories, such as the Vera C. Rubin Observatory in Chile. This facility is focused on mapping the Milky Way and beyond using a technique known as gravitational lensing. When light from distant galaxies passes near massive objects, such as clusters of dark matter, it bends. By measuring this distortion, scientists hope to locate and understand the distribution of dark matter across the universe, unveiling its properties and role in cosmic evolution. Meanwhile, particle physics experiments like those at the Large Hadron Collider, LHC in Switzerland, are striving to detect potential dark matter particles. Through high-energy collisions, scientists examine the aftermath of these interactions, searching for signs of exotic particles that might offer clues about dark matter's composition. In addition, underground laboratories such as the Large Underground Xenon, LUX, and LUX Zeppelin projects are attempting to capture dark matter particles using ultra-sensitive detectors shielded from the interference of cosmic rays. On the other side of the cosmic puzzle, dark energy continues to be explored through initiatives like the Dark Energy Survey. By mapping the distribution and movement of hundreds of millions of galaxies, cosmologists are trying to better understand dark energy's role in shaping the ultimate fate of the universe. Each new study and observation brings us closer to a clearer picture of these invisible forces. The quest for answers is relentless, fueling curiosity and excitement, not only among scientists but also among the broader public, eager to comprehend the deepest mysteries of the universe. In a seemingly unrelated but deeply interconnected development, scientists have begun studying extremophiles, remarkable organisms that thrive in environments once thought to be uninhabitable. These life forms are capable of surviving in conditions of extreme temperature, acidity, salinity, or pressure. Their existence challenges our understanding of life's boundaries and opens new possibilities for what defines life itself. Some extremophiles are capable of flourishing in boiling hot springs, in the frigid depths of the ocean, or in the face of radiation levels that would be lethal to humans. This ability suggests that life could, in theory, exist under similar extreme conditions on other celestial bodies, such as the icy moons of Jupiter and Saturn, or even on distant exoplanets. As a result, extremophiles are reshaping the criteria we use to search for life beyond Earth, encouraging us to broaden our expectations of habitability and consider environments that might once have seemed too hostile. Beyond expanding our understanding of life's potential across the cosmos, extremophiles also offer valuable insights into the biochemical pathways that sustain life. Many of these organisms utilize unique metabolic processes that allow them to extract energy from their harsh surroundings. For example, some can convert sulfur or methane into energy, a process that challenges our traditional notions of life's chemical foundations. These discoveries are not merely academic, they are crucial for expanding the possibilities of extraterrestrial life, pushing the boundaries of what we thought was possible in the search for life beyond Earth. The study of these resilient organisms and the ongoing exploration of dark matter and dark energy highlight a shared theme. The universe is full of unexpected mysteries, each one revealing new layers of complexity. As our scientific tools and methods improve, the once mysterious forces of dark energy and dark matter, as well as the astonishing adaptability of extremophiles, bring us closer to unraveling the vast and intricate tapestry of the cosmos. These discoveries are not only reshaping our understanding of the universe, but also propelling us forward into the unknown, where new and even more profound mysteries await. The study of extremophiles on Earth has opened a remarkable chapter in both biotechnology and astrobiology. These organisms, thriving in the most hostile environments imaginable, ranging from boiling hot springs to sub-zero Arctic ice, possess adaptations that not only allow them to survive, but to flourish where other life forms could not. Their resilience, however, is not just a curiosity, it's a valuable resource for human innovation. In the field of biotechnology, extremophiles are being harnessed to develop novel enzymes that can withstand industrial processes such as high-temperature reactions, or even help engineer crops that are far more resistant to the challenges of climate change, drought, and disease. But the impact of extremophiles reaches far beyond the laboratory. In fact, These remarkable organisms are reshaping our understanding of life's resilience in ways that go beyond Earth itself. By studying extremophiles, we are expanding the boundaries of what we thought was possible, not only in our own biosphere, but also in the search for life beyond our planet. The study of extremophiles has dramatically expanded our definitions of life, forcing us to rethink our assumptions about where and how life might exist elsewhere in the universe. Life's tenacity, it turns out, is far more extensive and adaptable than we ever imagined, raising questions that stretch the limits of our scientific imaginations. This new understanding of life is particularly important as we continue our quest to uncover extraterrestrial life, especially on Mars. The search for life on the red planet is not just about answering a single question. It's about challenging everything we think we know about biology. To help unravel this mystery, scientists and engineers are working tirelessly to design instruments capable of operating in some of the most extreme conditions known to humankind. These instruments, such as those aboard Mars rovers like Curiosity and Perseverance, are powered by a range of voltages, typically from 5 to 24 volts. These carefully selected voltages are essential for ensuring that the sophisticated machinery on these rovers, lasers, spectrometers, and soil analyzers can function efficiently, even in the harsh Martian environment. This careful balance of energy efficiency and power capacity is crucial. Instruments like Curiosity and Perseverance are equipped with tools that can perform incredibly complex analyses, such as determining the chemical composition of Martian rocks and soil. These findings could offer tantalizing clues about whether life ever existed on Mars. But operating these tools requires a delicate energy balance, especially since these rovers rely on solar panels to generate power, and Mars's harsh conditions often mean long periods of darkness and extreme temperatures. As a result, efficient energy management is essential, ensuring the rovers can continue their life-detecting missions even when Martian winters set in, when temperatures can plummet to dangerous lows. The voltage systems aboard these rovers are not just designed to perform their scientific tasks, but to endure the very environment they are meant to study. The ability to survive Martian winters while still collecting and transmitting data demands robust engineering solutions, and even a small disruption in the power supply can have catastrophic consequences. Yet, with every volt of energy that powers the rover's instruments, scientists edge closer to answering one of humanity's most profound questions. Are we alone in the universe? Beyond Mars, the icy moons of our solar system present another tantalizing frontier in the search for extraterrestrial life. Moons like Europa orbiting Jupiter and Enceladus orbiting Saturn harbor secrets beneath their frozen surfaces. These moons are thought to harbor vast hidden oceans beneath thick layers of ice, which could provide the perfect conditions for life to thrive. In 1995, scientists first theorized that Europa's icy surface might hide an ocean of liquid water beneath, and since then, evidence has been mounting to support this hypothesis. Beneath its icy crust, Europa is believed to harbor a salty ocean in contact with a rocky seafloor. This interaction between water and rock creates a rich chemical environment, potentially powered by geothermal energy, much like the hydrothermal vents found deep in Earth's oceans, places where life exists despite extreme conditions. Could similar environments exist on other worlds? The possibility ignites hope that Europa might harbor microbial life, or at least the conditions necessary for life to arise. Enceladus further fuels this optimism. In 2005, scientists detected plumes of water vapor shooting out from the moon's surface, carrying with them organic molecules, salts, and other chemicals potentially linked to habitability. The discovery that these plumes also contained organic molecules, the very building blocks of life, has raised the prospect that Enceladus's subsurface ocean might support life. The icy moons of our solar system are no longer distant, frozen bodies, but rather intriguing and promising frontiers in our quest for life beyond Earth. The study of these moons does more than just hint at the potential for extraterrestrial life. It challenges our understanding of where life can exist. Life on Earth has proven itself to be remarkably adaptable, thriving in environments that were once thought inhospitable, deep in the ocean, high in the atmosphere, or even in the hottest deserts. If life can endure in such diverse environments on Earth, who's to say it couldn't survive in places with conditions we once considered extreme? These icy moons serve as key laboratories, expanding our understanding of the kinds of environments that could foster life beyond our planet, and suggesting that the cosmos might be teeming with possibilities. But sending missions to these distant worlds presents a set of enormous challenges. The distance itself is one of the greatest obstacles. A journey to Mars, our next-door neighbor in the solar system, takes around 6 to 8 months. Yet, if we look further out to the gas giants like Jupiter and Saturn, travel times can stretch to several years. Planning missions to these distant worlds requires not just innovative propulsion systems, but also strategies for sustaining spacecraft and their instruments for years, or even decades on end. Communicating with spacecraft is another critical challenge. The distances involved mean that signals take considerable time to travel back and forth. For instance, a message to Mars takes around 13 minutes to reach Earth, while a signal to Neptune can take over 4 hours. This delay in communication poses significant challenges for mission control. Without real-time communication, engineers on Earth cannot respond immediately to unexpected problems or adjustments. Spacecraft must be equipped to operate autonomously, making critical decisions on their own in real time without waiting for instructions from Earth. In the face of these challenges, human ingenuity continues to push the boundaries of what's possible. Each new mission, whether to Mars, Europa, or beyond, brings us closer to understanding the answers to questions that have captivated humanity for centuries. Is there life beyond Earth? What does life look like elsewhere in the cosmos? And ultimately, what does it mean for us as a species to be part of this vast, unexplored universe? The answers lie far beyond the stars, in the icy depths of distant moons and the barren landscapes of Mars, waiting for us to find them. The harsh environments of distant planets present significant challenges for space exploration, each obstacle demanding innovative solutions and advanced technology. For example, ice giants like Uranus are subjected to extreme cold, while planets such as Jupiter experience intense radiation. These conditions require equipment that is not only highly specialized, but also durable enough to withstand a range of environmental stresses, from freezing temperatures to corrosive atmospheres. To ensure the success of missions to these distant worlds, the instruments must be meticulously tested to guarantee they can endure these punishing conditions. The testing process, often rigorous and prolonged, increases both the cost and the development timeline of space missions. In addition to environmental challenges, the unpredictable nature of space itself adds a further layer of complexity. Asteroids, solar flares, and unforeseen technical malfunctions can threaten to derail even the most meticulously planned missions. Therefore, mission planners must develop strategies to address a range of contingencies. This includes ensuring that both crew members and instruments are equipped to adapt swiftly to rapidly shifting conditions. The uncertainties of space exploration are ever present, but they do little to diminish the excitement that the quest to explore distant planets brings. Despite these daunting obstacles, the pursuit of knowledge about our solar system remains one of humanity's most thrilling frontiers, promising profound discoveries that could reveal the deepest mysteries of our cosmic neighborhood. Astrobiologists, tasked with uncovering the potential for life beyond Earth, rely on a combination of astronomical observations, chemical analysis, and theoretical models to predict the habitability of exoplanets in faraway star systems. At the heart of this search is the concept of the habitable zone, the region around a star where conditions might be suitable for liquid water to exist. Water is considered a vital ingredient for life as we know it, making the identification of planets within this zone a top priority for scientists. Once a planet is identified as a potential candidate, the focus shifts to studying its atmosphere. By examining how starlight interacts with the planet's atmospheric layers using cutting-edge instruments on telescopes, scientists can detect gases that may signal biological activity. For example, the presence of oxygen or methane in substantial quantities could suggest that life is active on that planet as we observe similar phenomena here on Earth. Beyond atmospheric composition, astrobiologists also investigate other key factors that could support life, such as the planet's temperature, surface conditions, and geological activity. A rocky world, orbiting within the habitable zone of a stable star, is more likely to foster the development of life. The type and age of the star also play crucial roles in determining a planet's potential habitability. Stars that are too bright or too erratic may not offer the stable conditions necessary for life to flourish. The study of extreme environments on Earth, such as deep-sea hydrothermal vents or icy landscapes in the Arctic, also provides valuable insights. By understanding how life forms can survive in these harsh, remote environments, scientists can extend their search for life to similar conditions on other planets. This ongoing exploration, driven by curiosity and scientific rigor, continues to push the boundaries of what we know about life in the universe. It also fuels our imagination, inspiring the belief that life may be out there, waiting to be discovered on distant worlds. The quest to understand the potential for life beyond Earth is a journey that has only just begun, yet it holds the promise of answers to one of humanity's most profound questions. Meanwhile, cosmic rays, high-energy particles traveling through space, also present both a mystery and a challenge for space exploration. These particles can occasionally collide with Earth's atmosphere, creating a cascade of secondary particles with various effects. One of the most intriguing aspects of cosmic rays is their ability to influence weather patterns. They can contribute to the formation of clouds in the atmosphere, subtly impacting climate conditions on Earth. Additionally, cosmic rays pose a threat to the electronic systems aboard satellites, causing disruptions and malfunctions in the data they collect. The origins of cosmic rays are diverse and fascinating. Some of these particles are produced by our own sun, especially during solar flares and coronal mass ejections, which charged particles blasting through space. However, the most energetic cosmic rays come from sources beyond our solar system. These include supernova explosions, neutron stars, and black holes in distant galaxies. The energies of these particles can be millions of times greater than those achieved by the most powerful particle accelerators on Earth. Intriguingly, about 1 in every 5 cosmic rays that reach Earth's surface consists of protons, with the rest made up of heavier elements like helium nuclei and even more massive atomic nuclei. These heavier particles are sometimes referred to as heavy cosmic rays. Fortunately, Earth's magnetic field and atmosphere act as a protective shield, blocking many of these high-energy particles. However, a small fraction does make it to the surface, where they can lead to unique and fascinating scientific phenomena. Researchers continue to study cosmic rays in order to better understand their behavior, origins, and effects on our planet. These particles play an essential role in astrophysics, and studying them helps us gain a deeper understanding of the universe. As our knowledge of cosmic rays expands, so too does our understanding of the cosmos and the intricate forces that shape it. The Fermi paradox presents a perplexing question that continues to intrigue scientists and philosophers alike. Despite the vastness of the universe and the sheer number of stars similar to our sun, we have yet to find any definitive evidence of extraterrestrial civilizations. The name of the paradox comes from the renowned physicist Enrico Fermi, who famously asked, "Where is everybody?" during a conversation about the possibility of intelligent alien life. This paradox leads to a range of theories about the nature of extraterrestrial life and its potential existence. One theory posits that intelligent life may be exceedingly rare, with the specific conditions required for life to thrive being so unique that they are unlikely to be replicated elsewhere in the universe. Factors such as the right distance from a star, suitable atmospheric conditions, and the planet's geological stability may be rare combinations. If this is the case, the silence of the cosmos could be explained by the sheer improbability of life emerging on another planet. Another possibility is that intelligent civilizations are more common than we think, but they tend to self-destruct before they have the chance to explore or communicate with other civilizations in the galaxy. This theory suggests that the very technological advancements that allow a civilization to explore space may also lead to its downfall, whether through nuclear warfare, climate change, or other catastrophic events. These civilizations could wipe themselves out before they make contact with others. In this context, the absence of extraterrestrial communication could serve as a cautionary tale, a reminder of the dangers that accompany technological progress. The Fermi paradox, therefore, remains one of the most thought-provoking questions in the search for extraterrestrial life. It challenges our assumptions and invites us to reflect on the future of our own civilization, urging us to consider both the possibilities and the potential perils of advancing technology. As we continue to search the stars for signs of life, the paradox reminds us of the mysteries that still lie waiting to be uncovered in the vast expanse of the cosmos. The universe, in all its vastness, may be teeming with life in ways we cannot yet fathom. There's a curious, enigmatic suggestion that we might not even recognize the signs of life when we encounter them. Extraterrestrial civilizations could be communicating in forms that are completely beyond our perception, or perhaps they are deliberately choosing not to interact with us for reasons that remain entirely beyond our understanding. This opens up the possibility that the cosmos is brimming with life, hidden right before our eyes, life that we are utterly blind to because we are operating with parameters that simply don't capture the full spectrum of intelligence or communication. The famous Fermi paradox forces us to confront an uncomfortable question. If the universe is so vast and filled with potential for life, why haven't we made contact? It challenges not only our assumptions about life beyond Earth, but also the very definition of existence. It's a profound prompt that forces us to consider not only the possibility of life elsewhere, but the entire nature of being itself. One of the most intriguing phenomena discovered in recent years is the mysterious occurrence of fast radio bursts, FRBs. These brief yet intense pulses of radio waves are among the most fascinating objects in modern astrophysical research. First detected just over a decade ago, FRBs last only milliseconds but release an astonishing amount of energy, equivalent to what our sun emits in an entire day. Despite their sudden appearance and powerful release of energy, the origins of these bursts remain a profound mystery, making them an irresistible subject of investigation. Every new FRB detected offers a fresh piece to the cosmic puzzle, providing unique insights into the most extreme and perplexing events in the universe. One key lesson gleaned from studying FRBs is their ability to probe the interstellar medium, offering a window into the unseen aspects of the universe. As these bursts travel across vast stretches of space, their signals are distorted, delayed, and scattered. These variations provide valuable clues about the density, composition, and distribution of matter throughout the cosmos. By examining the ways in which these signals are dispersed and altered by the space they travel through, scientists can infer the makeup of invisible matter, such as dark matter, that permeates the universe. This information has the potential to drastically refine our models of how the universe evolved and how it is structured. However, while there has been progress in understanding the basic mechanisms behind FRBs, they still present a number of unresolved mysteries. The exact origin of these bursts is still uncertain. Some scientists speculate that they might be the result of magnetars, hypermagnetic neutron stars, while others have proposed more exotic ideas, such as interactions with dark matter. Each of these potential explanations opens up a new set of questions, propelling researchers to investigate not only the physical processes that give rise to FRBs, but also the fundamental nature of the cosmos itself. The elusiveness of these bursts keeps scientists on edge, spurring the development of more advanced tools and observatories in the hope that one day we might uncover the secrets hidden within these brief high-energy flashes. The ongoing study of FRBs does more than just expand our knowledge of extreme astrophysical events, it also encourages a deeper inquiry into the very principles that govern our universe. Each new burst detected opens a new chapter in the cosmic narrative, sparking our imagination and pushing us to ask what else is out there beyond the visible horizon of space. One of the most awe-inspiring structures in the universe is the cosmic web, a sprawling, interconnected network that governs the distribution of galaxies and matter on the grandest scales. This web consists of vast, intricate filaments composed of dark matter and gas. It serves as the very scaffolding of the universe, connecting galaxies across incomprehensible distances. If you imagine a spider's web, the strands would represent these filaments, and the intersections would be where galaxies and superclusters are found. At the heart of this web lie regions of high density, called nodes, where galaxies come together in large, tightly packed clusters. These clusters are not randomly distributed, but are aligned along the cosmic filaments, with dark matter acting as the structural framework that guides their formation. The cosmic web's filamentary structure influences the motion of galaxies, affecting how they form and evolve over billions of years. As galaxies travel along these filaments, they interact with each other, exchanging gas and fueling the formation of new stars. The web does more than shape the locations of galaxies. It plays a crucial role in how matter is distributed throughout the universe. Regions with higher concentrations of dark matter lead to stronger gravitational interactions, which can trigger the formation of new galaxies or cause existing ones to merge. Understanding the cosmic web is essential for unlocking the mysteries of galactic evolution, and it provides critical insights into how the universe has evolved since the Big Bang. As we continue to explore the cosmic web, astronomers are gaining a deeper understanding of the fundamental physics that underpin the universe's structure. This exploration helps us appreciate the complexity of the cosmos and the intricate forces at play, guiding us through the long journey from the Big Bang to the universe as we know it today. Dark flow, another fascinating phenomenon, further complicates our understanding of the cosmos. This enigmatic movement suggests that some galaxy clusters are being pulled toward a specific area of space, in a direction that cannot be explained by the standard expansion of the universe. This motion appears to be oriented radially toward a region beyond the observable universe, a concept that has captivated astronomers and cosmologists alike. The implications of dark flow are profound. If some galaxy clusters are moving in a trajectory unlike anything predicted by the current models of cosmic expansion, it suggests that there are enormous and hidden structures influencing their motion. These structures could be superclusters of galaxies or even vast cosmic filaments acting as a gravitational pull that is affecting the universe on a scale far beyond our current observational capabilities. This discovery challenges the idea that the universe is isotropic or uniform in all directions. Instead, dark flow could indicate that the universe's large-scale structure is far more interconnected and complex than we previously realized. Moreover, dark flow raises questions about the boundaries of our observable universe. If there are vast structures beyond the reach of our current instruments, it forces us to rethink the limits of human observation in cosmology. It invites us to reconsider the nature of cosmic inflation and the way in which matter and energy are distributed throughout the universe. This discovery pushes us to look beyond the visible horizon, to explore the unknown, and to expand our search for answers to the great mysteries of existence. Dark flow serves as a reminder of the vastness and the untapped potential for discovery that lies beyond our current understanding of the universe. It challenges us to embrace the unknown and to push the boundaries of what we think is possible. As we explore this phenomenon further, we may gain critical insights into the formation and evolution of cosmic structures, deepening our understanding of the forces that shape our universe. Every new piece of the cosmic puzzle, whether it's the mysteries of dark flow, the discovery of FRBs, or the study of the cosmic web, adds to the ever-expanding narrative of the universe. These discoveries spark our curiosity and ignite our desire to explore the infinite reaches of space. And as we continue this journey, we may one day unlock answers to the fundamental questions about existence itself. The ultimate fate of the universe has been a subject of intense speculation for generations. What will become of this vast, expanding expanse of matter and energy? Several theories have emerged, each shaped by our understanding of cosmic expansion, dark energy, and the fundamental forces that govern the cosmos. One of the most widely discussed theories is the Big Freeze, or heat death. According to this hypothesis, as the universe continues to expand, it will become increasingly cold and dark. Stars will burn out, galaxies will drift apart, and the universe will approach a state of maximum entropy, where no energy gradients will exist to sustain any physical processes. In this scenario, the universe will become a cold, lifeless expanse. In contrast, there is the Big Crunch, a theory that suggests that if the density of matter in the universe is high enough, gravitational forces might eventually slow the expansion of the universe, causing it to collapse back in on itself. This dramatic reversal could lead to a singularity where all matter and energy are compressed into an infinitely small point. This collapse could potentially lead to another Big Bang, offering the possibility of a cyclical universe where cosmic life cycles through periods of expansion and contraction. Another possibility is the Big Rip, a hypothesis driven by the increasing role of dark energy in the universe's accelerated expansion. If dark energy continues to grow stronger, it could eventually tear apart galaxies, stars, and even atomic structures, leading to a catastrophic end where the very fabric of spacetime itself is ripped apart. Each of these theories paints a starkly different picture of the universe's ultimate fate, offering visions of either a cold, empty expanse, a dramatic collapse, or a violent tearing apart of reality itself. However, no matter the outcome, these theories highlight the awe-inspiring complexity of the universe and our place within it. They push us to confront the most profound questions about existence, time, and the nature of the cosmos itself. The answers may remain elusive, but the search for them will continue to shape our understanding of the universe for generations to come. The notion of a cyclic universe offers a radical departure from our traditional view of cosmic beginnings and endings. Instead of envisioning a single beginning and inevitable end, this theory proposes that the universe undergoes infinite cycles, each defined by periods of expansion and contraction. Every cycle may begin with a Big Bang, only to eventually end in a Big Crunch, only to begin anew. This concept challenges the conventional understanding of linear time, offering an image of a universe in perpetual motion. The cosmos would be continuously evolving in phases, each cycle contributing to the larger, ongoing story of existence. The exploration of the universe's potential fate has long captivated scientists and philosophers. Two primary theories have dominated the discussion: the Big Crunch and heat death. The Big Crunch presents a scenario in which the universe eventually reverses its current expansion. Here, the gravitational pull of matter gradually overcomes the repulsive force of dark energy, slowing down the universe's expansion. Eventually, galaxies, stars, and all forms of matter would collapse back into a singularity, essentially a point of infinite density, much like the event that started it all with the Big Bang. In this dramatic conclusion, the universe might undergo a form of cosmic rebirth, resetting itself and beginning a new cycle of existence. In contrast, the heat death scenario presents a far more subdued, gradual demise. According to this theory, as the universe continues to expand, stars will eventually exhaust their nuclear fuel. Over countless billions of years, this will lead to the slow dimming of the cosmos. Galaxies will drift apart, and the temperature of the universe will approach absolute zero. The heat death of the universe would mean that no new stars will form, and existing celestial bodies will fade away, leaving behind a cold, lifeless void. In this scenario, the universe reaches a state of maximum entropy, where all energy is uniformly distributed, making it impossible for any complex processes or structures to emerge. While the Big Crunch suggests a dramatic end of collapse, heat death represents a slow, silent extinguishing of the cosmos, like the final flicker of a dying light. What makes these scenarios particularly fascinating is how they reflect our understanding of the fundamental forces that govern the universe. As new observational data pour in, especially from distant galaxies and cosmic radiation, scientists continue to debate which of these scenarios may ultimately prevail. The universe's fate may well surprise us, revealing new mysteries about the very fabric of existence. In the process, we may deepen our understanding of the cosmos in ways we never imagined. Amid these discussions of the universe's ultimate end, the idea of a cyclical universe suggests that our cosmos may not be a one-time phenomenon at all. Instead of the widely accepted view of a singular Big Bang, followed by continuous expansion, the cyclic theory posits that the universe undergoes an endless series of cycles. Evidence for this theory comes from various fields of study, including observations of cosmic microwave background radiation and the distribution of galaxies across space. One of the most compelling pieces of evidence lies in the characteristics of cosmic microwave background radiation, which is a remnant from the universe's early stages. Some scientists speculate that slight irregularities in this radiation could indicate multiple phases of universal evolution, possibly pointing to cycles of rebirth. Furthermore, gravitational waves and dark energy provide additional clues, suggesting that the universe's behavior may be far more complex than we once thought. These phenomena could indicate the potential for an oscillatory universe, one that moves through regular cycles of birth, death, and rebirth. This concept aligns with theories in string theory and quantum gravity, which propose that the fundamental forces of the universe may allow it to go through these cycles. For example, some models suggest that the end of one universe could create the necessary conditions for the next to emerge. While the mainstream view of cosmology supports a single Big Bang event, these alternative theories are gaining increasing traction as observational tools become more advanced and our understanding of the universe deepens. The prospect of a cyclical universe challenges our current perspectives on cosmology and invites further exploration of the cosmos. This ongoing exploration of the universe's cyclical nature feeds directly into our broader understanding of cosmic evolution. The life cycle of stars, for instance, plays a central role in shaping the future of galaxies. Stars form from clouds of gas and dust, burn through their nuclear fuel over millions or billions of years, and ultimately die, releasing elements into space that influence the formation of new stars and planets. This cycle of stellar birth, life, and death not only shapes the stars themselves, but also dictates the evolution of entire galaxies. The death of massive stars, for instance, results in supernova, which scatter heavy elements across space, enriching the interstellar medium and influencing the formation of new stars. As stars evolve, they also affect the gravitational dynamics of their galaxies. The interactions between stars, such as the formation of binary star systems or stellar collisions, can have profound impacts on a galaxy's structure. These interactions can lead to phenomena such as gamma-ray bursts, the formation of neutron stars, and the creation of black holes. Each of these events provides valuable feedback that influences the future star formation rates within a galaxy. By integrating this knowledge into sophisticated simulations, scientists are able to make more accurate predictions about when and how a galaxy will experience bursts of star formation or gradual declines over the course of billions of years. Understanding stellar evolution is thus a key piece of the larger puzzle of cosmic evolution. As we gain deeper insights into how stars shape galaxies, we can make more informed predictions about the future of our own Milky Way galaxy, as well as countless others scattered throughout the cosmos. In many ways, the story of stars is also the story of galaxies, revealing the intricate, interconnected nature of the universe. In addition to these theoretical pursuits, humanity's growing ability to explore the cosmos makes the idea of inhabiting other celestial bodies increasingly plausible. Advances in space technology are paving the way for more ambitious missions beyond Earth. Traditional chemical propulsion systems, while effective, are limited by their speed and efficiency. New propulsion concepts, such as ion propulsion and nuclear thermal propulsion, could significantly reduce travel times to distant destinations like Mars or the moons of Jupiter and Saturn. These innovations promise to enhance the feasibility of sending humans to explore these far-off worlds, pushing the boundaries of space exploration. Equally critical to long-duration space travel is the development of life support systems. The harsh conditions of space present significant challenges to human survival, but closed-loop life support systems, which recycle air and water, are becoming more advanced. Prototypes of these systems are already being tested aboard the International Space Station, and their continued development will be essential for future missions to distant planets and moons. These innovations bring us closer to realizing the dream of exploring and potentially inhabiting other worlds, ensuring that the story of human exploration continues to unfold alongside the grand narrative of the universe itself. In recent years, the technological advancements necessary for humanity to live and thrive beyond Earth have become a focal point of both scientific exploration and public fascination. As we envision a future where humans can settle on distant worlds, innovations in areas such as food production, habitat construction, and energy generation are key to creating sustainable colonies on other planets. Space agencies and private companies alike are working tirelessly to overcome the many challenges of extraterrestrial living. One critical development is the ability to grow food in space, a task that could dramatically alter the way astronauts live during long missions. Hydroponics and aeroponics, the soil-free methods of growing plants, could become the foundation for growing nutritious food on Mars, the Moon, or beyond, addressing the pressing need for self-sufficiency. These methods are not only effective but efficient, allowing astronauts to cultivate a variety of crops that can sustain them for extended periods, creating a long-term, reliable food source far from Earth. At the same time, habitat construction technologies are advancing, making it increasingly possible to build permanent homes on alien worlds. The concept of 3D printing, in particular, offers promising potential for constructing habitats using materials found directly on other planets. For example, lunar regolith, soil found on the Moon, or Martian soil could serve as the building blocks for creating shelters, thereby reducing the enormous cost and complexity of transporting materials from Earth. This process would make construction on distant planets far more feasible and efficient, as it relies on local resources instead of having to carry everything from Earth. In addition to 3D printing, inflatable habitats are also being explored as an adaptable, lightweight, and transportable solution for space settlements. These habitats can be easily compressed for launch and then expanded once they reach their destination, providing a flexible and scalable way to create living spaces on planets where traditional building methods are impractical. As with any human endeavor in space, power generation is a fundamental concern. Sustainable energy sources are crucial to supporting life on distant planets, where conventional infrastructure is absent. Solar panels, for example, could provide a renewable energy source on planets like Mars or the Moon, where sunlight is abundant, but at varying intensities. In more challenging environments, nuclear reactors might be necessary, providing a consistent and reliable power supply to support everything from life support systems to robotic exploration vehicles and scientific research equipment. These advancements in energy production will play a pivotal role in humanity's ability to establish permanent colonies on extraterrestrial worlds, paving the way for the next great chapter in our journey as a species. These innovations are more than just theoretical. They represent the building blocks of humanity's ambitions to become a multiplanetary species. As we begin to master these technologies, they will make the dream of space colonization a tangible reality, allowing us to venture into the far reaches of the cosmos. Parallel to these advancements in space exploration, the fascinating field of quantum mechanics continues to challenge and reshape our understanding of the universe. One of the most intriguing phenomena in quantum mechanics is quantum entanglement, a concept that seems to defy everything we know about locality, the idea that objects are only directly influenced by their immediate surroundings. According to classical physics, if two particles are separated by vast distances, any interaction between them should be confined to local effects. However, quantum entanglement challenges this principle by revealing that when two particles become entangled, the state of one particle is instantaneously linked to the state of the other, no matter how far apart they are. This means that a change in one particle will immediately affect its entangled partner, an idea that appears to violate the speed limits set by the speed of light. Albert Einstein famously referred to this phenomenon as spooky action at a distance, expressing his skepticism about the implications of entanglement. Yet, despite Einstein's reservations, experiments have consistently demonstrated that entangled particles do indeed exhibit this instantaneous correlation, indicating that the universe does not strictly adhere to the classical laws of locality that we once believed were inviolable. As scientists continue to explore the depths of quantum mechanics, it becomes clear that quantum entanglement holds profound implications for technology and the future of human communication. One of the most promising applications of quantum entanglement is in the field of quantum computing. Unlike classical computers, which process information in binary form using bits, quantum computers harness the principles of superposition and entanglement to process information in ways that classical computers cannot. This has the potential to revolutionize fields such as cryptography, medicine, and artificial intelligence, solving problems that are currently beyond the reach of even the most powerful supercomputers. Additionally, quantum entanglement is central to the development of quantum cryptography, which promises to create unbreakable encryption systems that use the entangled states of particles to protect information. As data security becomes an increasingly pressing concern in our digital age, these advances could offer unprecedented levels of protection against cyber threats. But quantum mechanics isn't just a gateway to new technologies. It also prompts deep philosophical questions about the nature of reality. Quantum entanglement suggests that the universe is far more interconnected than we ever imagined, blurring the line between objects that are physically distant from each other. It invites us to reconsider the very foundations of our understanding of the cosmos, challenging us to think about what it truly means for something to exist. The implications of quantum entanglement go beyond mere scientific curiosity. They force us to examine the underlying nature of existence itself, opening up new realms of thought that intertwine science and philosophy. In the early universe, quantum fluctuations played a vital role in shaping the cosmos as we know it. During the first moments after the Big Bang, the universe was an incredibly hot and dense energy soup, a chaotic environment where the laws of quantum mechanics dominated. In this primordial state, tiny fluctuations in energy were constantly appearing and disappearing, a phenomenon known as quantum fluctuations. These fluctuations were not just random noise, they represented the very seeds of the universe's structure. As the universe expanded and cooled, these tiny energy variations were stretched across vast distances by the rapid inflationary period that followed the Big Bang. This rapid expansion magnified the fluctuations, ultimately leading to the formation of galaxies, stars, and other cosmic structures. In essence, quantum fluctuations provided the initial imperfections in the universe, allowing matter to accumulate and form the galaxies and clusters we observe today. Moreover, these fluctuations are believed to contribute to the cosmic microwave background radiation, the faint afterglow of the Big Bang that we observe in the present day. The small variations in the temperature of this radiation provide a snapshot of the universe's early state, giving scientists valuable insights into its origins and the forces that shaped its evolution. The study of quantum fluctuations underscores the intricate relationship between quantum mechanics and cosmology. It reveals how the fundamental laws of physics govern not only the behavior of subatomic particles, but also the vast, complex structures that make up the universe. These fluctuations were instrumental in forming the cosmic landscape, and their study continues to inform our understanding of the origins of the universe. Quantum mechanics also challenges our traditional notions of observation and reality itself. The observer effect, a phenomenon central to quantum theory, suggests that the mere act of observation can influence the behavior of quantum particles. In other words, when we measure or observe a quantum system, its properties appear to change, highlighting a profound and puzzling aspect of reality. This phenomenon has sparked numerous debates about the nature of existence. Does reality exist independently of our observation, or is our perception an integral part of its existence? Different interpretations of quantum mechanics have emerged to address this question, including the Copenhagen interpretation, which posits that physical systems do not have definite properties until they are observed, and the many worlds interpretation, which suggests that all possible outcomes of a quantum event occur in parallel universes, rendering observation irrelevant. These debates have far-reaching implications for our understanding of reality, as they challenge the very foundations of how we perceive the world around us. The observer effect reminds us that the universe may not be as straightforward or as objective as we once assumed. The act of observation itself may play a fundamental role in shaping the reality we experience, and this insight invites us to explore the strange and enigmatic nature of the quantum world. Lastly, quantum tunneling, a phenomenon where particles can pass through barriers that classical physics would deem insurmountable, provides another example of the bizarre and counterintuitive behavior exhibited by subatomic particles. One of the most intriguing areas where quantum tunneling is observed is in the process of nuclear fusion within stars. In the cores of stars, hydrogen atoms fuse together to form helium, releasing vast amounts of energy. According to classical physics, the electromagnetic repulsion between the positively charged protons should prevent them from getting close enough to undergo fusion. Yet, thanks to quantum tunneling, these particles can tunnel through the energy barrier, allowing fusion to occur and fueling the stars that light up the universe. Through phenomena like quantum tunneling, we gain a deeper understanding of the complex and often paradoxical nature of the universe, one that defies our conventional expectations and invites us to explore the mysteries of existence at the most fundamental level. These quantum phenomena challenge our understanding of the cosmos and provide a glimpse into the strange, beautiful world that lies beneath the surface of our everyday experiences. Quantum tunneling, a fascinating phenomenon in the world of quantum mechanics, allows certain particles like protons to pass through energy barriers that classical physics would deem impassable. This seemingly magical process facilitates nuclear fusion even at temperatures far lower than classical theories would predict. In fact, quantum tunneling plays a crucial role in explaining how stars, like our very own sun, shine. It is not only central to the life cycles of stars, but it is also involved in the explosive processes that occur when massive stars exhaust their nuclear fuel. As these stars collapse under their immense gravitational pull, quantum tunneling becomes a key player in electron capture and neutronization, processes that are essential for forming heavier elements through explosive nuclear synthesis. By studying these quantum effects, astrophysicists gain insights into the formation of elements that scatter across the universe. These elements are the building blocks of planets, and by extension, life itself. But the scope of quantum tunneling doesn't stop at stellar phenomena. It extends into the formation of some of the universe's most enigmatic structures, like supernova and neutron stars, where the collapse of a massive star into a dense core leads to the creation of new, extremely dense forms of matter. As scientists dive deeper into the study of quantum mechanics, they continue to refine their understanding of the cosmos and its origins. One area where quantum tunneling proves invaluable is in theories about black holes and the early universe. Cosmic inflation, the rapid expansion of space immediately following the Big Bang, is a phenomenon that can be better understood through the lens of quantum mechanics. Tiny quantum fluctuations in the early universe may have led to the large-scale structures we see today. These fluctuations could have profound implications, helping shape the very nature of the universe's vast framework. Through continued exploration of quantum tunneling, scientists not only unravel the mysteries of space and time, but also discover new connections between the microscopic world of quantum mechanics and the macroscopic world of the universe. This ongoing journey of discovery highlights the indispensable role that quantum mechanics plays in our understanding of the universe. Quantum mechanics itself is a branch of physics dedicated to uncovering the behavior of the smallest particles in the universe. It offers a lens through which scientists examine the fundamental building blocks of matter. Unlike classical physics, which describes the universe in terms of deterministic rules, quantum mechanics reveals that particles exist in a state of probability. Rather than being certain about a particle's position or momentum, scientists can only predict the likelihood of finding it in a particular state. One of the most groundbreaking ideas in quantum mechanics is superposition. In this principle, particles can exist in multiple states at the same time until they are measured. This paradoxical concept is foundational in high-energy physics experiments, like those conducted at particle colliders. When particles collide at immense speeds, they create extreme conditions that can give rise to entirely new particles. These collisions allow scientists to probe the fundamental forces of nature and perhaps even reveal new forces or dimensions that were previously undetected. Equally captivating is quantum entanglement, the phenomenon where particles become intertwined so that the state of one particle can instantly influence the state of another, no matter how far apart they are. This interconnection could point to hidden dimensions of spacetime or new forms of interaction that extend beyond our four-dimensional understanding of the universe. Scientists are exploring theories that could expand our comprehension of gravity, electromagnetism, and other forces. These efforts may one day lead to the discovery of new particles, potentially unlocking new chapters in our understanding of the universe. At the heart of these pursuits lies the ambition to unite various theories of physics into a more unified framework. As physicists continue to probe the mysteries of quantum mechanics, they are inching closer to answering profound questions about the nature of the universe, its origins, and its future. Each new insight into the quantum world brings with it possibilities that fuel the imagination and curiosity of scientists and cosmologists alike. In recent decades, technological advancements have dramatically changed our ability to observe the universe. The development of sophisticated telescopes both on Earth and in space has allowed astronomers to peer further into the cosmos than ever before. Equipped with highly sensitive sensors, these telescopes can detect faint light and electromagnetic radiation from distant stars and galaxies, unveiling objects that were once invisible to the human eye. One of the most significant advancements came with the launch of the Hubble Space Telescope in 1990. Positioned above Earth's atmosphere, Hubble is free from the distortion caused by atmospheric turbulence, allowing for unparalleled clarity in observations. This vantage point has led to groundbreaking discoveries, including the realization that the expansion of the universe is accelerating. Hubble has also played a pivotal role in identifying exoplanets, planets located outside our solar system, and has provided vital data on the structure and evolution of the cosmos. More recently, space-based observatories have become even more advanced, expanding our understanding of deep space. In addition to optical telescopes like Hubble, new technologies such as radio telescopes and gravitational wave detectors are providing fresh insights into cosmic phenomena. Radio astronomy, for example, has revealed the cold, dark corners of the universe, capturing signals from cosmic background radiation and pulsars. Meanwhile, gravitational wave observatories like LIGO, Laser Interferometer Gravitational Wave Observatory, are opening a new frontier in our understanding of the universe, detecting the ripples in space-time caused by cataclysmic events such as black hole mergers and neutron star collisions. These advancements are not just enhancing our ability to observe the universe, they are democratizing access to these cosmic phenomena. Data collected by observatories is being shared with researchers around the world, as well as with the general public. This collaborative approach is accelerating discovery and transforming our understanding of the universe. As technology advances, we edge ever closer to answering the profound questions about the nature of existence and the origins of the cosmos. The Hubble Space Telescope, in particular, has revolutionized our understanding of deep space. By providing incredibly clear images of distant galaxies and stellar nurseries, Hubble has enabled scientists to probe the farthest reaches of the observable universe. One of its most critical contributions was determining the rate of expansion of the universe, which has been crucial in understanding its age and size. Hubble's observations have also played a central role in the discovery of dark energy, a mysterious force that is causing the universe's expansion to accelerate. These discoveries have opened up entirely new areas of study in cosmology, enriching our knowledge of the universe's fundamental workings. As technology and scientific understanding continue to evolve, the cosmos unfolds in ever more astonishing ways, each breakthrough providing a deeper look into the mysteries of existence and the very fabric of reality itself. The Hubble Space Telescope has fundamentally reshaped our understanding of the cosmos, acting as a critical tool for astronomers in uncovering the many mysteries of the universe. Through its unparalleled ability to observe distant stars, galaxies, and nebulae, Hubble has provided insights into the life cycle of stars and galaxies, revealing the complex processes of stellar evolution from birth to death. By capturing the various phases of stellar formation, Hubble's observations have illuminated the intricate dance of gas, dust, and energy that gives rise to new star systems. Among the most captivating of Hubble's contributions are its breathtaking images of nebulae, vast clouds of gas and dust, the very building blocks of stars. These vivid snapshots, often bursting with colors and intricate structures, are more than just scientific data. They are a gateway to understanding the origins of stars and the fundamental processes that fuel the universe. With every image, Hubble not only expands our scientific knowledge, but also sparks public interest in space exploration. The intricate details portrayed in these cosmic photographs invite viewers to reflect on the immense scale of the universe and humanity's place within it. Each photograph from Hubble acts as a reminder of the universe's awe-inspiring complexity and beauty, continuously fueling our curiosity. They challenge us to ask deeper questions about what lies beyond our tiny planet, urging us to ponder the unknown. One of the most profound revelations from Hubble's extensive research comes from the study of supernova, particularly Type 2A supernova. These stellar explosions, which occur in binary systems where one star is a white dwarf, have provided critical insights into the expansion of the universe. When a white dwarf accumulates enough mass from its companion star, it reaches a critical threshold and explodes. These stellar bursts, extremely bright and consistent in their luminosity, serve as standard candles, a tool used to measure astronomical distances. By observing the brightness of these supernovae, scientists can calculate their distance from Earth. When these measurements are compared to the redshift of the light, an effect caused by the stretching of light waves as the universe expands, they gain valuable information about the rate at which the universe is expanding. The surprising discovery from this research was that, rather than slowing down, the expansion of the universe is actually accelerating. This led to the hypothesis of dark energy, a mysterious force that opposes gravity and is believed to drive this acceleration. This groundbreaking finding has profoundly altered our understanding of cosmology, challenging scientists to rethink the fundamental forces at play in the universe. Each supernova, as a cosmic beacon, serves as a guidepost, helping scientists chart the universe's expansion and refine their models of cosmological evolution. The relationship between distance, redshift, and the expansion of the universe is complex and deep, opening new avenues of research into the universe's past, present, and future. As astronomers continue to explore these cosmic phenomena, each new discovery brings us one step closer to unlocking the fundamental secrets of the universe. In December 2021, the James Webb Space Telescope, JWST, was launched, marking a monumental leap forward in humanity's quest to understand the universe. Designed to observe the cosmos in infrared light, JWST is capable of seeing deeper into space and further back in time than any telescope before it. This advanced capability allows scientists to probe celestial phenomena that were previously hidden behind dense clouds of gas and dust, offering an unprecedented view into the formation of stars, galaxies, and planetary systems. One of the most exciting aspects of the JWST is its potential to shed light on the earliest moments of the universe, particularly the formation of the first stars and galaxies after the Big Bang. By detecting the faint light emitted by these ancient objects, astronomers hope to gain insights into how these early cosmic structures evolved over billions of years. This research could provide answers to some of the most fundamental questions about the origins of the universe and the processes that led to the complex structures we observe today, including our very own Milky Way galaxy. Beyond its role in exploring the distant universe, JWST is also equipped to study exoplanets, planets that exist outside our solar system. By analyzing the atmospheres of these distant worlds, the telescope can detect the presence of elements such as water, carbon dioxide, and even potential signs of life. This opens up exciting possibilities for understanding the conditions that might support life on planets far beyond Earth, broadening the scope of our search for life in the universe. The significance of the James Webb Space Telescope goes far beyond its technical innovations. It symbolizes humanity's insatiable curiosity and our collective drive to comprehend the vast, awe-inspiring universe we inhabit. Each new discovery made by JWST has the potential to rewrite our understanding of astrophysics, while also sparking new questions and ideas. As the telescope journeys further into the depths of space, we stand on the precipice of remarkable revelations about the universe's past, present, and perhaps even its future. However, astronomers face unique challenges when interpreting the data gathered by extraterrestrial telescopes, such as Hubble and JWST. The sheer volume of data collected by these space-based observatories is staggering. With each observation spanning multiple wavelengths of light, the task of sifting through this data to identify meaningful patterns requires immense computational power and sophisticated processing algorithms. Often, a significant amount of time is spent simply organizing the data before analysis can begin. Another key challenge is the calibration of these instruments. Unlike ground-based telescopes, which can be adjusted and repaired more easily, space telescopes operate in the unforgiving environment of outer space. Factors like temperature fluctuations, cosmic radiation, and even micrometeoroid impacts can influence the sensitivity and accuracy of these instruments. Ensuring that the data is properly calibrated so it accurately reflects astronomical events is critical for successful interpretation. This meticulous process often requires the use of complex models that predict and compensate for the various environmental effects that could distort the data. Despite these challenges, the data collected by these extraordinary telescopes continue to expand our knowledge of the universe. Every discovery brings us one step closer to understanding the cosmos and our place within it, further igniting our curiosity and drive to explore the mysteries of space. Through the combined efforts of the Hubble Space Telescope, the James Webb Space Telescope, and the tireless work of astronomers, we continue to push the boundaries of human knowledge, uncovering the secrets of the universe, one discovery at a time. Astronomers must constantly grapple with the limits of our understanding of the universe. The vastness of space is filled with celestial objects that behave in ways that challenge and even defy the theories we have long established. As our instruments improve and we make new discoveries, we find that many of the phenomena we thought we understood demand further examination. For example, the discovery of exoplanets has opened up a new world of questions, not only about the composition of these distant worlds, but also about the possibility of atmospheres and the potential for life beyond Earth. These discoveries often force scientists to rethink old ideas, pushing the boundaries of our knowledge. Each new finding leads to new questions, urging researchers down unfamiliar paths of inquiry. In some cases, these paths require the development of new technologies, tools that allow us to explore the cosmos in ways we never imagined possible. However, the journey of scientific discovery is not one taken alone. Collaboration is at the heart of this work. Astronomers rarely work in isolation. They are part of interdisciplinary teams that include physicists, engineers, and data scientists. These teams share insights, pool their expertise, and approach problems from different angles, ultimately helping to illuminate the complexities of the data they analyze. By working together, they help to unravel the mysteries of the universe, advancing our understanding of the cosmos, and even ensuring that the challenges posed by extraterrestrial telescopes lead to groundbreaking discoveries. The formation of our solar system is an epic tale that began over 4.5 billion years ago. It's a story filled with intrigue, one that scientists are still piecing together today. At its core, the story begins with a massive cloud of gas and dust, known as a solar nebula, that eventually collapsed under its own gravity. This collapse led to the formation of the Sun at the center, surrounded by a swirling disk of material. From this disk, the planets, moons, asteroids, and comets we know today were formed. Yet many questions remain about how exactly these celestial bodies came into being. Why does our solar system have such a distinct arrangement of planets? The inner planets, Mercury, Venus, Earth, and Mars, are small and rocky, while the outer planets, Jupiter, Saturn, Uranus, and Neptune, are massive and gas-rich. Scientists have put forward several theories to explain this distribution. One of the leading ideas involves temperature differences within the protoplanetary disk. These temperature variations would have influenced how and where different materials could condense, leading to the formation of the varied types of planets we see today. But there are still many mysteries to uncover, especially regarding the presence of water and other essential elements. How did water, a crucial ingredient for life as we know it, find its way to the inner planets? One hypothesis suggests that icy bodies, like comets and asteroids, may have delivered water to the inner solar system after the planets had already formed. But the timeline of this delivery and the chemistry behind it are still actively debated among scientists. Then there's the mystery of Planet 9, an elusive entity that has yet to be seen but is theorized to exist beyond Neptune. Astronomers have noticed strange orbital patterns among distant objects in the Kuiper belt, suggesting that the gravitational pull of an unseen planet could be at play. But does this represent a single unknown planet, or perhaps a collection of smaller bodies? This remains one of the great unknowns in astronomy, and every new discovery pushes us closer to understanding it. Our understanding of the solar system's formation continues to evolve, as each discovery brings us one step closer to answering some of its biggest questions. These mysteries remind us that the cosmos is full of profound, unanswered questions just waiting to be explored. Looking beyond our solar system, the environments of Venus and Mars offer striking examples of how different conditions can shape evolution of planets. Venus, often referred to as Earth's twin due to its similar size and composition, has followed a vastly different path. With a thick atmosphere composed mainly of carbon dioxide, Venus experiences a runaway greenhouse effect that has driven its surface temperatures to nearly 800 degrees Fahrenheit, hot enough to melt lead. The crushing atmospheric pressure only compounds the inhospitable conditions, making it a world seemingly hostile to life, as we know it. Yet, despite this extreme environment, the planet's geological features, such as vast plains and towering volcanic structures, hint at a history of volcanic activity, offering scientists clues about its past and how it arrived at its current state. In contrast, Mars presents a much cooler and drier landscape. Once thought to be a twin of Earth, Mars has since revealed extensive evidence of past water flows, with ancient river valleys and lake beds that suggest a wetter climate in its distant past. However, the planet's thin atmosphere, composed mainly of carbon dioxide with very little pressure, prevents liquid water from existing on its surface for long. Any water present quickly evaporates or freezes, leaving behind a barren world. The study of Mars poses significant challenges to the idea of habitability. As scientists continue to study how Mars' climate changed from one that could have supported life to the desolate environment we see today, they are uncovering vital clues about the processes that shape planetary climates and the conditions needed for life to thrive. These two planets, Venus and Mars, serve as poignant examples of planetary evolution. Their differing conditions were influenced by a combination of factors: proximity to the sun, atmospheric composition, and geological activity, all of which contributed to their unique evolutionary paths. For Venus, its close proximity to the sun likely led to its harsh conditions, while Mars, being farther out, faced its own set of challenges. Together, these two planets underscore the delicate balance of factors that influence planetary development and highlight the complex interplay between a planet's position in the solar system, its atmosphere, and its potential for supporting life. Studying the differences between two planets in our solar system is not just a matter of comparing their physical characteristics. It's an exploration that provides invaluable insights into the formation and evolution of our entire cosmic neighborhood. This comparison helps us piece together the history of our solar system, from its chaotic beginnings to its current configuration. But the lessons extend far beyond our own planetary system. As we explore these contrasting environments, we unlock new possibilities in the search for life beyond Earth. Each planet tells a story, its evolution shaped by a myriad of physical and chemical processes. These planets, each a unique world, offer a window into the diversity of planetary environments that populate our universe. In a way, the planets in our solar system are like ancient manuscripts waiting to be read, revealing details about how they formed, what conditions shaped them, and how they might evolve in the future. This ongoing investigation is not only essential for understanding Earth's place in the cosmos, but also for guiding our search for habitable worlds around distant stars. Comets and asteroids, often regarded as cosmic relics, are like time capsules that offer us a direct link to the early solar system. These objects hold a wealth of information about the solar system's formation, helping us understand the conditions that existed billions of years ago. Our system was born. When our solar system, around 4.6 billion years ago, it was a wild, chaotic place filled with gas, dust, and countless small icy and rocky bodies. The comets and asteroids we see today are remnants of this primordial chaos. By studying them, scientists can piece together what the building blocks of planets might have been and what conditions prevailed during their formation. Asteroids are primarily found in the asteroid belt, which lies between Mars and Jupiter. These rocky remnants are considered leftovers from the formation of the inner planets, Mercury, Venus, Earth, and Mars. When scientists examine the compositions of various asteroids, they can determine the types of minerals and compounds present in the early solar system. Some asteroids contain organic compounds and minerals, hinting at the processes that occurred in the solar system's infancy. For instance, certain carbon-rich asteroids may hold clues about the chemical ingredients necessary for life. These discoveries are of particular interest to scientists, as they suggest that life's basic building blocks may have existed in the solar system long before Earth became habitable. Comets, on the other hand, come from the colder outer reaches of the solar system, particularly from the Kuiper Belt and the Oort cloud, which lie far beyond Neptune. When comets approach the sun, they begin to heat up, releasing gas and dust that form a glowing tail. This dramatic outburst offers astronomers the chance to study the volatile compounds contained within comets, water and organic molecules that are essential for life as we know it. The very presence of these compounds in comets raises intriguing questions about the origins of Earth's water and whether the building blocks of life were delivered here from deep space. In the grand scheme, these small bodies, asteroids and comets, are more than just fascinating objects in the sky. They are cosmic messengers, offering us a glimpse into the early solar system and revealing the diverse paths through which planetary systems evolve. As we continue to explore them through missions and observatories, scientists are uncovering the secrets of our cosmic history. Each discovery adds a layer to our understanding of how the solar system formed, how it has changed over time, and how other systems might evolve, potentially harboring life. The study of exoplanets, planets orbiting stars beyond our sun, has been one of the most groundbreaking scientific endeavors of recent decades. A few decades ago, the notion of planets orbiting distant stars was largely confined to the realm of science fiction. Now, we know of thousands of exoplanets, each with its own unique features. These discoveries have not only revolutionized our understanding of planets, but they have also challenged many of our previous assumptions about what constitutes a planet. One of the most astonishing revelations has been the wide variety of planetary systems that exist in our galaxy. Many exoplanets orbit their stars in configurations radically different from the ones we observe in our own solar system. Some are found in close orbits, subjected to extreme temperatures and conditions that seem hostile to life as we know it. Others are part of multi-planet systems, where planets orbit close together, creating intricate gravitational interactions. These systems provide a stark contrast to our own, where the planets are more spread out and the gravitational dynamics are less chaotic. This has led to important questions. Is our solar system an anomaly, or is it one of many different types of planetary architectures in the galaxy? The study of exoplanets has also provided new insights into the formation and evolution of planetary systems. By examining distant worlds, scientists can better understand the processes that occur in young star systems, how dust and gas come together to form planets, and how these planets evolve over time. The sheer diversity of exoplanets observed has forced scientists to rethink earlier models of planet formation, which were often based on the idea that planets could only form in certain ways. Now, it's clear that planets can form in many different ways, with a variety of outcomes depending on the conditions in their home systems. Perhaps the most tantalizing aspect of the search for exoplanets is the quest to find Earth-like planets, worlds that could support life. The discovery of potentially habitable exoplanets has reinvigorated discussions about the origins of life, both here on Earth and elsewhere in the universe. Researchers are paying particular attention to planets in the habitable zone, the region around a star where conditions might allow liquid water to exist on a planet's surface. In our own solar system, the search for life extends beyond Earth. Scientists are looking at Mars and moons like Europa to see if life might have once existed, or could still exist on those worlds. The study of exoplanets not only broadens our understanding of the universe, but also forces us to reconsider our place within it, sparking the age-old question, are we alone? The gas giants Jupiter, Saturn, Uranus, and Neptune are a cornerstone of planetary science, offering essential clues about how planets form and evolve. These massive worlds differ greatly from the smaller rocky planets in the inner solar system. They are primarily composed of hydrogen and helium, with deep atmospheres and large, often mysterious cores. Their immense size and unique composition make them key to understanding the processes that govern planetary formation. One of the most intriguing aspects of gas giants is their ability to attract and hold on to large amounts of gas and dust from the early solar system. This ability to accumulate material played a crucial role in their growth, shaping their size and composition. For example, Jupiter's massive gravity allowed it to capture far more gas than smaller planets like Earth. This, in turn, had a profound effect on its atmosphere, as well as its potential for supporting life. Understanding how these gas giants formed and how they interact with the rest of the solar system provides scientists with valuable insights into the dynamics of planetary systems, both within our own solar system and beyond. Each new discovery about gas giants, asteroids, comets, and exoplanets adds to the rich tapestry of knowledge that scientists are weaving about the cosmos. As we continue to push the boundaries of exploration, we deepen our understanding of not only where we came from, but where we might be headed in the search for life elsewhere in the universe. Furthermore, studying the gas giants offers profound insights into planetary migration. Research has shown that in the early stages of our solar system's formation, gas giants may have shifted considerably from their original positions due to powerful gravitational interactions. These migrations might hold the key to explaining the current arrangement of the planets within our system. What's more, they provide a broader understanding of how other planetary systems across the galaxy might have evolved. This revelation underscores the importance of studying gas giants, as their movement could help scientists decode the complex dynamics that govern planetary behavior in other distant systems. In addition to their role in understanding planetary migration, gas giants often host intricate systems of moons and rings. These structures are not just visually captivating, but serve as a natural laboratory for examining the processes of planetary formation and evolution under varying conditions. By studying these systems, researchers are able to expand their knowledge not only of the gas giants themselves, but also of the diverse and often surprising characteristics that can emerge within planetary systems. This deeper understanding, in turn, enhances our ability to theorize not just about the formation of our own solar system, but also about the processes that could shape other distant planetary systems far beyond our reach. However, exploring phenomena such as these can be challenging. Many aspects of the universe are not directly observable, and scientists often need to rely on indirect evidence to build their theories. This is especially true for enigmatic phenomena like black holes and dark matter. To uncover their secrets, physicists must turn to data gathered from related phenomena, experiments, and advanced statistical analysis. For instance, though we cannot directly observe black holes, we can study their effects on nearby stars and gas. By carefully tracking the movements and behaviors of these objects, scientists are able to infer the presence of these unseen giants, along with their key properties. A critical tool in this process of inference is the use of theoretical models. These models serve as frameworks, predicting how the universe should behave based on our understanding of the fundamental laws of physics. When new experimental data or observational evidence presents discrepancies with existing models, scientists are able to refine and adjust them. One key example of this process is the discovery of cosmic microwave background radiation, which provided critical indirect evidence for the Big Bang theory. This breakthrough offered a powerful confirmation of our current understanding of the universe's origins, highlighting the role of indirect evidence in shaping our scientific understanding. Mathematicians also play a pivotal role in this endeavor. By developing equations that express relationships between measurable quantities, they help physicists make predictions about phenomena that are not directly observable. Take gravitational waves, for example. These ripples in the fabric of spacetime were first predicted by Albert Einstein's theory of general relativity. However, they went undetected until years of indirect measurements, and only in recent years have we been able to directly observe them. This confirmed Einstein's theory in a spectacular way, offering further insights into the nature of gravity and expanding our understanding of the universe. The combination of observation, mathematical modeling, and theoretical predictions provides a powerful approach for piecing together the universe's secrets. In many ways, this process mirrors that of detectives working to solve a mystery, using clues and evidence to gradually unravel a larger story. By continuing to delve into these unknowns, scientists are steadily unlocking the mysteries of the cosmos. Bridging the gap between the observable and the unseen, computer simulations have become indispensable tools in modern astrophysics. They allow scientists to explore cosmic phenomena that might otherwise remain beyond the reach of direct observation. Many processes that occur in the vast expanse of space, such as the formation of galaxies, the evolution of stars, and the behavior of black holes, are far too complex to study through traditional observational techniques. Computer simulations allow researchers to model these processes virtually, using the known laws of physics to predict outcomes under various conditions. One of the most powerful aspects of computer simulations lies in their ability to handle vast quantities of data. By inputting different variables into their models, researchers can simulate different conditions and observe how these changes impact the evolution of cosmic events. For example, in studying galaxy formation, simulations can take into account the gravitational influence of dark matter, the dynamics of gas clouds, and the rates at which stars form. This allows scientists to watch galaxies evolve over billions of years, all within a fraction of real time. Simulations also provide crucial insights into phenomena that are challenging to observe directly, such as black holes. Since black holes cannot be seen with visible light, scientists rely on simulations to model the gravitational effects these objects have on their surroundings. By doing so, they gain important insights into the behavior and properties of black holes, helping to test and refine fundamental theories, including general relativity. Moreover, these simulations are key in predicting future astronomical events, guiding observational campaigns, and helping scientists focus their telescopic efforts on areas of greatest interest. The growing sophistication of computer simulations has greatly advanced our understanding of the universe. As technology improves, these simulations become increasingly accurate, incorporating more variables and offering greater insight into cosmic phenomena. This synergy between simulation and observational astronomy represents a hallmark of modern astrophysical research. Through this collaboration, scientists not only expand their knowledge of the universe, but also spark new questions and avenues for exploration, pushing the boundaries of our understanding in the process. Without the use of computer simulations, our understanding of the cosmos would be far less comprehensive. These tools have become integral in studying the universe, offering us a way to peer into regions of space that would otherwise remain obscured, all while raising new questions about the very nature of reality. A significant challenge in modern physics is the quest to reconcile two of the most fundamental theories in science, general relativity and quantum mechanics. Developed by Albert Einstein, general relativity describes gravity as the warping of space and time around massive objects. This elegant theory explains the behavior of large-scale cosmic structures, from planets to galaxies. Yet it falls short when it comes to explaining the behavior of matter and energy at the smallest scales, where quantum mechanics rules supreme. Quantum mechanics, in contrast, governs the behavior of particles, forces, and energies at microscopic scales. It is a realm defined by uncertainty, randomness, and probabilistic events, elements that stand in stark contrast to the deterministic and smooth nature of general relativity. The challenge scientists face is finding a way to unite these two vastly different frameworks. One promising approach to bridging this divide is string theory, which proposes that the fundamental building blocks of the universe are not point-like particles but tiny vibrating strings. These strings can create different particles and forces, providing a potential framework that unifies gravity with quantum mechanics. Another intriguing possibility is loop quantum gravity, which suggests that space-time itself is quantized, composed of tiny loops woven into the fabric of the universe. This theory challenges our traditional understanding of space as a smooth continuum and proposes a new way of thinking about the very nature of the cosmos. Both string theory and loop quantum gravity, along with other emerging ideas, aim to offer a deeper understanding of phenomena such as black holes, the early universe, and the fundamental nature of reality. Though the journey toward a complete theory of quantum gravity remains uncertain, the ongoing exploration of these ideas enriches our understanding of the universe. Each new discovery brings us closer to understanding the deep, interconnected nature of space, time, and everything within them. In recent years, significant breakthroughs in astronomy have led to new debates and questions, challenging long-established theories of the universe. One notable example is the detection of gravitational waves in 2015, which provided strong confirmation of Einstein's theories of relativity. These ripples in space-time not only validated Einstein's predictions, but also opened up new avenues for exploring the most elusive and mysterious aspects of the cosmos. However, subsequent discoveries have revealed even more complex phenomena that challenge and expand our understanding of black holes and the very nature of gravity itself. These new insights suggest that there is still much to learn about these enigmatic cosmic objects that have captivated scientists and philosophers alike for centuries. One of the most striking developments concerns the expansion of the universe. Initially, astronomers thought that gravitational forces would eventually slow down the rate at which the universe was expanding. Yet measurements from distant supernovae and the cosmic microwave background radiation unveiled an astonishing revelation. The universe's expansion is not slowing, but actually accelerating. This unexpected finding led to the theory of dark energy, a mysterious force pushing the cosmos to expand faster. The exact nature of dark energy remains one of the most perplexing challenges in modern astrophysics, sparking numerous models and theories vying for scientific consensus and clarity. Meanwhile, the study of exoplanets, planets that orbit stars at our solar system, has taken a remarkable leap forward. Advanced telescopes, such as the Transiting Exoplanet Survey Satellite, TESS, have allowed astronomers to identify thousands of these distant worlds, many of which reside in the so-called habitable zone. This is the region around a star where conditions might be right for liquid water to exist, a fundamental requirement for life as we know it. The discovery of these potential Earth-like planets raises profound questions about the prevalence of life in the universe and challenges existing theories about planet formation and the conditions necessary for life. Can life exist in environments vastly different from Earth? Are we truly alone, or are we one among many? In addition to these strides in planetary science, technological innovations in imaging have revolutionized our understanding of some of the universe's most mysterious phenomena. The Event Horizon Telescope's groundbreaking achievement, capturing the first ever image of a black hole's shadow, has reverberated through the scientific community, sparking fresh discussions about black hole formation, behavior, and the fundamental forces of nature. These new imaging techniques allow astronomers to test long-held theories and confront the unknown, highlighting the ever-evolving nature of astronomical research. Each discovery opens a new door, often leading to even deeper questions about the universe and our place within it. Interdisciplinary collaboration has become increasingly vital in addressing these complex cosmic puzzles. Drawing knowledge from diverse fields, such as physics, astronomy, biology, and even art, scientists are now able to approach astronomical phenomena from multiple perspectives. This collective wisdom fosters connections that may not be immediately obvious through the lens of a single discipline. For example, the intersection of physics and biology encourages the exploration of how life might survive in extreme environments, far beyond the conditions we are familiar with on Earth. Similarly, the collaboration between astronomers and computer scientists, powered by advanced algorithms and high-tech simulations, enables researchers to visualize and analyze the most complex cosmic events, from galaxy formation to the inner workings of black holes. These simulations make abstract concepts more tangible and provide an invaluable tool for testing scientific theories. For example, high-powered computational models help us understand the dynamics of galaxy evolution, the behavior of stars, and the gravitational forces that shape the universe. Meanwhile, philosophers engage in profound discussions about the implications of these discoveries, exploring existential questions about the nature of life, the universe, and human consciousness. These dialogues between science and philosophy help bridge the gap between empirical data and the abstract concepts that have long intrigued humanity. Moreover, the convergence of chemistry and astrophysics has paved the way for groundbreaking discoveries about the composition of celestial bodies. By analyzing the chemical signatures emitted by distant stars and planets, scientists can discern their potential to support life and unravel their origins. This synergy between disciplines enriches our understanding of the cosmos, propelling our curiosity about our place within it. Each discipline adds another layer of depth, enhancing our comprehension of the universe's intricate beauty and complexity. As we venture further into the cosmos, the blending of diverse fields ignites our imagination and fuels an insatiable thirst for knowledge. This multidisciplinary approach reveals a universe that is far more complex and awe-inspiring than we had ever imagined. It calls upon us to dig deeper, asking more questions, challenging old paradigms, and embracing the mysteries that continue to unfold before us. Throughout human history, the cosmos has been a powerful source of inspiration for artists and creators alike. From the earliest cave paintings depicting celestial bodies to contemporary works that explore the vastness of space, the universe has continuously shaped our imagination. Ancient civilizations, for example, observed the stars and planets not only to guide their agricultural practices, but also to weave them into myths and legends, illustrating humanity's intrinsic connection to the cosmos. During the Renaissance, artists like Leonardo da Vinci began incorporating scientific ideas into their work, blending artistic expression with the pursuit of knowledge. The groundbreaking discoveries of this period, such as the heliocentric model proposed by Copernicus, inspired artists to contemplate cosmic order and humanity's place within the expansive universe. This era produced masterpieces that captured the wonder of the stars, utilizing perspective and light to evoke the vastness of the heavens. In the Romantic period, artists explored the sublime nature of the cosmos, with painters like Caspar David Friedrich using the night sky to evoke powerful emotions of transcendence and awe. The Romantic movement also gave birth to literature inspired by the stars, as writers and poets grappled with humanity's place in a seemingly infinite universe. The themes of beauty and mystery dominated this literary landscape, as creators sought to understand the infinite, often finding solace and meaning in the vast, uncharted territories of space. Today, modern artists and filmmakers continue to be inspired by the grandeur of the universe, whether through breathtaking depictions of distant galaxies in film or public art installations that integrate astronomy. The cosmos remains an inexhaustible well of creativity. As our understanding of the universe deepens through scientific exploration, our artistic expressions evolve, reflecting our ongoing quest to comprehend our place in this vast, mysterious cosmos. The cosmos has also had a profound influence on literature and film, fostering a rich body of work that explores themes of space, time, and humanity's existence. One of the most iconic examples is Arthur C. Clarke's novel 2001: A Space Odyssey, published alongside Stanley Kubrick's film of the same name. The story delves into humanity's evolution, artificial intelligence, and the mysterious monoliths that guide human destiny, encapsulating the awe and wonder of space exploration. Another remarkable work is Carl Sagan's Contact, which beautifully merges science and philosophy. In this novel, Dr. Ellie Arroway discovers a signal from an extraterrestrial civilization, raising profound questions about the nature of the universe and humanity's search for meaning in the grand scheme of existence. Sagan's ability to convey complex scientific concepts with elegance has made Contact a landmark in popularizing the cosmos. On the cinematic front, films like Christopher Nolan's Interstellar have pushed the boundaries of visual storytelling, tackling themes like time dilation, black holes, and human survival. Interstellar not only takes viewers on a visually stunning journey through space, but also explores the emotional connections that bind us. The film highlights love as a force so powerful that it transcends time and space, blending scientific rigor with deeply human emotion. Another iconic creation is The Twilight Zone, the timeless science fiction series created by Rod Serling. Through its anthology format, the show explored cosmic themes, alternate realities, and moral dilemmas, often against the backdrop of vast, otherworldly settings. Each episode left viewers with more questions than answers, perfectly capturing the mysterious and unpredictable nature of the universe. Finally, the study of ancient astronomy has profoundly shaped how we interpret the cosmos today. These early observations laid the groundwork for the modern scientific understanding of the universe and continue to inspire new generations of astronomers, artists, and thinkers. The search for meaning in the stars is an enduring human endeavor, one that transcends science and art, binding us together in our collective journey to explore the unknown. From the Babylonians to the Greeks and Mayans, ancient civilizations devoted immense attention to the night sky, using it not only for practical purposes but also for cultural and spiritual meaning. These early astronomers meticulously charted the movements of celestial bodies, linking their observations to agriculture, navigation, and most importantly, mythology. Their skywatching wasn't a simple scientific endeavor. It was a way to understand the world and their place within it. Through storytelling, they wove cosmic events into the very fabric of their cultural identities, explaining the seasons, creation, and moral lessons through vivid mythic narratives. For example, constellations were not just collections of stars in the night sky. They were transformed into characters, gods, heroes, and creatures, each with a distinct story that offered both explanations and lessons. These tales helped people make sense of the universe and its rhythms, often emphasizing the cycles of nature, moral virtues, and the larger forces at play in the cosmos. This blend of scientific observation with mythological interpretation created a rich tapestry of knowledge that not only guided ancient societies, but also continues to resonate in cultures around the world today. As we advanced in our scientific understanding of the universe, many of these ancient astronomical concepts continued to linger in our everyday language and thought. Take, for instance, the term retrograde, used to describe the apparent backward motion of planets. This phrase, along with others, is a linguistic relic from early astronomers who, despite lacking modern tools, made profound observations about the stars. They recognized patterns and cycles in the heavens with remarkable precision, insights that still hold value in contemporary astronomy. Furthermore, ancient astronomical philosophies left an indelible mark on modern cultural and spiritual beliefs. Many indigenous cultures, for instance, still honor celestial cycles with a deep respect, viewing the movements of the stars, planets, and moons as integral to their connection with the Earth. Rather than seeing humanity as separate from the cosmos, these perspectives emphasize harmony and interconnectedness. The idea that we are not merely passive observers of the universe, but active participants in a grand cosmic dance, challenges us to rethink how we interact with the world around us. In this view, the natural world and its celestial counterparts are not distant or foreign. They are part of our shared experience, intimately tied to the rhythms of life. This ancient wisdom also stirs a renewed sense of wonder in modern society. Today, as we stand on the shoulders of the early stargazers, our quest to understand the cosmos continues to draw on the same inquisitive spirit that inspired them. The pursuit of knowledge, whether through scientific inquiry or artistic expression, echoes the curiosity and wonder that have always been central to human experience. Our exploration of the universe is not simply about gathering facts, it is a way of engaging with the mystery and beauty of existence itself. Indeed, myths and legends have long been powerful tools for understanding our place in the universe. Ancient civilizations looked to the sky and spun tales to explain the mysteries above. The Greeks, for example, saw their gods and goddesses represented in the constellations, turning the heavens into a canvas for human narratives. These stories merged the divine and the natural, offering both comfort and meaning. They helped people navigate the uncertainties of life, providing a sense of community through shared stories passed down through generations. As these stories evolved, so too did our understanding of the cosmos. In Native American cultures, the stars were often regarded not as distant points of light, but as spiritual beings with whom humans shared a profound connection. The Milky Way was viewed as a pathway or river connecting Earth to the cosmos, symbolizing the relationship between humanity and the universe. These stories imbued the stars with purpose, urging people to see them not just as celestial bodies, but as guides and teachers. This perspective fostered a sense of stewardship for the land and the natural cycles that governed life, encouraging an awareness of the deep connection between human existence and the cosmos. In modern times, even as we have developed a more scientific understanding of the universe through telescopes, space missions, and quantum theory, the allure of mythic narratives endures. Our storytelling continues to blend scientific inquiry with metaphor and imagination. Concepts like black holes, the possibility of extraterrestrial life, and the nature of time often serve as the backdrop for modern myths, explored in literature, films, and other media. These stories retain their power because they speak to something universal, our innate desire to understand the unknown, to explore the limits of our knowledge, and to seek meaning in the vastness of space. Ultimately, the myths and legends of the past teach us that our journey through the cosmos is not just a scientific pursuit, but a deeply human one. They remind us that the exploration of space is as much about our imagination, our dreams, and our fears as it is about the hard data collected by astronomers. These stories are the threads that connect us across time and space, helping us navigate the unknown with a sense of wonder and humility. As we gaze up at the stars, we are reminded that, in many ways, the quest to understand the universe is a reflection of our own search for meaning, purpose, and connection. Scientific discoveries about the universe have not only advanced our knowledge of the cosmos, they have also reshaped contemporary philosophical debates. The realization that our universe is vast, constantly expanding, and likely teeming with mysteries challenges many traditional ideas about existence. For centuries, humanity thought of the cosmos as a static, unchanging entity. Now we know it is dynamic and ever-evolving, prompting us to reconsider our place within it. This shift in understanding raises profound philosophical questions about the nature of time, causality, and infinity. If the universe is in constant flux, what does this mean for the idea of permanence? How do we come to terms with the idea that our existence is part of a much larger, ever-changing cosmos? Moreover, breakthroughs like the discovery of black holes or the potential existence of multiple universes directly impact discussions about determinism and free will. If our universe is just one of potentially countless others, what does that mean for the choices we make? Are our actions truly our own, or are they part of a grand cosmic plan? These ideas raise fundamental questions about the nature of free will and the meaning of personal agency. Are we merely actors in a cosmic drama, or do we have the power to shape our own destinies? At the same time, the scientific understanding of our Earth as a fragile, isolated oasis in the midst of a vast and indifferent universe has had a profound impact on ethical and moral thought. The realization that our planet is unique, perhaps even rare, has spurred many to rethink our relationship with it. As we peer into the cosmos and recognize the vastness of space, we are reminded of the fragility of our existence. This perspective has led to a reevaluation of our responsibilities toward the planet and one another, urging us to consider the long-term consequences of our actions. It prompts us to ask difficult questions about our role in the preservation of life, not just for ourselves, but for all living beings and future generations. In this way, the scientific study of the cosmos has inspired a more inclusive, holistic ethical framework, one that transcends human concerns and embraces the broader ecological interconnectedness of all life. In the intricate landscape where science and philosophy converge, an intriguing potential for dialogue unfolds. Philosophers probe the implications of scientific theories, while scientists find inspiration in the profound, sometimes elusive, questions that philosophy raises. This dynamic interplay enriches our collective understanding, not only of the cosmos, but also of our own place within it. It reveals a fundamental truth. The pursuit of knowledge is as much about inquiry and exploration as it is about wonder and contemplation. Through this lens, scientific breakthroughs don't merely expand the boundaries of what we know. They deepen our engagement with the age-old questions that define our existence. The concept of time, especially in cosmological models, offers a fascinating case study of this convergence between science and philosophy. Time is no longer a static, unchanging backdrop to the universe. It is now understood as a dimension that interacts with space in a way that revolutionized our perceptions. This view owes much to Albert Einstein's theory of relativity, which shattered the classical notion of time as an absolute constant. Instead, time is seen as fluid, varying with speed and gravitational influence. As a result, time behaves differently in different parts of the universe. For example, time slows down in stronger gravitational fields and speeds up in weaker ones. The practical effects of this phenomenon are evident even in everyday technology. Astronauts aboard the International Space Station experience a slight but measurable slowing of time compared to those on Earth. Such revelations challenge our intuitive grasp of time and lead to profound philosophical questions. What does it mean to experience time in such a varied way? How do these discrepancies in time's passage affect our understanding of the universe? These inquiries push the boundaries of both science and philosophy, inviting us to reflect on deeper existential matters. What is the nature of time itself? Will the passage of time change as the universe evolves? As space continues to expand and galaxies drift further apart, what role does time play in this cosmic dance? This inquiry into the nature of time also serves as a gateway to one of the most profound questions in cosmology, the existence and nature of the universe's edge. At first glance, we might imagine the universe as having an edge akin to the boundary of an ocean. However, our modern understanding tells us that the universe does not have a clear-cut boundary. Instead, it is expanding, with galaxies moving farther apart as space itself stretches. The observable universe, the part of the cosmos we can study, is defined by the distance light has traveled since the Big Bang, roughly 13.8 billion years ago. This gives us a limit to what we can observe, the observable universe. But beyond this observable horizon lies the unobservable universe, a domain that current scientific theories suggest extends far beyond our ability to measure or detect. We can infer that it is governed by the same physical laws that govern the observable universe, and likely contains countless galaxies, stars, and planets that remain hidden from us. This brings forth a fascinating set of questions. If the universe is infinite, does it really have an edge? Could it stretch on forever, beyond our reach or understanding? If so, what does it mean for our place in it? The concept of infinity itself challenges our deepest intuitions about space, time, and existence. The universe, as we understand it, may indeed extend without limit, an idea that is both humbling and awe-inspiring. Infinity pushes the very limits of human comprehension, forcing us to reckon with something that is beyond measurement and beyond our grasp. How do we make sense of a universe that is in some ways infinite? In our everyday lives, we deal with finite quantities, numbers, distances, time spans. But when faced with the prospect of an infinite universe, we are forced to confront our own inability to truly grasp the scale of what we're studying. Some scientists and philosophers venture into even more speculative territories, such as the idea of the multiverse. According to this theory, our universe may be just one of many, each with its own distinct set of physical laws and constants. This tantalizing idea stretches the imagination and raises even more questions about the nature of reality. If our universe is just one among countless others, what does that mean for our understanding of existence itself? Are we merely one thread in a vast and varied tapestry, or is our universe unique in ways that we cannot yet fathom? At the heart of these questions lies humanity's oldest and most enduring quest, the desire to understand our place in the cosmos. Despite the vastness of what remains unknown, each discovery brings us one step closer to uncovering the mysteries that lie beyond our observable horizon. With each new insight, we gain a deeper understanding of the universe's complexity, sparking wonder and curiosity that have driven human inquiry for millennia. Ultimately, the search for answers to these cosmic questions invites both scientists and philosophers to venture beyond the boundaries of the known world, to explore realms that challenge our understanding and spark our imagination. Whether it is the nature of time, the limits of the universe, or the possibility of other realities, these inquiries remind us that the journey of discovery is as much about the questions we ask as the answers we find. The mysteries of the cosmos are infinite, and so too are the possibilities for discovery and wonder. Infinity, a concept that stretches the limits of both understanding and imagination, lies at the heart of some of the most profound questions about the universe. The notion of infinity challenges our comprehension, especially when applied to cosmological theories about the universe's origin, structure, and ultimate fate. Questions that have long perplexed cosmologists include whether the universe has existed forever or whether it had a definitive beginning. If the universe is infinite, what implications does that have for the concept of time? Is time itself endless, or did it have to emerge from some origin point? This dilemma brings us to paradoxes that complicate our understanding of space and time. If infinity truly defines the universe, then the concept of a beginning seems to vanish, and with it, the idea of an end. Does this mean the universe exists without a fixed origin, or was there a singular moment in time when everything began, followed by an infinitely expanding cosmos? Such questions echo through the halls of theoretical physics and cosmology, suggesting that our current understanding of spacetime may not be sufficient to explain these vast mysteries. Equally compelling is the theory of the multiverse. The idea that our universe could merely be one of an innumerable number of others, each possibly distinct in their physical laws and properties, has captivated the imagination of physicists and philosophers alike. Some of these universes could be infinite in their own right, stretching the very definition of reality. As we contemplate infinity, we are drawn to reconsider what reality itself might mean. This idea forces us to confront the limits of our perception, the boundaries of human understanding, and the incredible depth of the mysteries that remain untapped. While the notion of infinity is perplexing, it also inspires awe. It sparks the curiosity of scientists who continue to investigate the very fabric of the universe. At the same time, it reminds us of the vastness of what we have yet to learn, urging us to continue our quest for answers. And yet, for all its challenges, infinity serves as a catalyst for exploration, driving the pursuit of knowledge deeper into the unknown. The laws of physics, fundamental as they are, provide the structure that governs the universe. These principles, such as gravity, motion, and thermodynamics, are the invisible hands that mold the cosmos, guiding the formation and evolution of stars, planets, and galaxies over time. Gravity, the force that holds the universe together, is the architect of the cosmos. It draws matter together, enabling the creation of celestial bodies from the smallest particles to the largest galactic clusters. This gravitational force shapes the very nature of stars, guiding their formation and evolution. For example, gravity is responsible for the creation of dense regions in space that eventually collapse into stars. As stars are born, they go through different stages of nuclear fusion, converting hydrogen into helium while releasing vast amounts of energy. This process not only fuels the luminosity of stars, but also influences their mass, size, and eventual life cycle. The delicate balance between the outward force of energy released during nuclear fusion and the inward pull of gravity determines whether a star will end its life as a red giant or explode in a spectacular supernova. These explosive events are far more than dramatic displays. They play a pivotal role in the universe's continual cycle of creation. Supernovae disseminate elements throughout the cosmos, contributing to the formation of new stars and planets. This process, known as stellar nucleosynthesis, ensures the creation of the very elements that form everything from new celestial bodies to the very atoms that make up our existence. Motion, too, plays an essential role in the behavior of celestial bodies. Isaac Newton's laws of motion and universal gravitation revealed how planets orbit stars and how moons orbit planets, providing a framework to understand the paths of objects in the cosmos. The same laws that predict the behavior of spacecraft trajectories also allow us to understand phenomena like tidal forces, which occur due to the moon's gravitational pull on Earth. These interactions shape the dynamics of celestial systems, including the formation of complex structures such as Saturn's rings or the intricate dance of moons around Jupiter. Thermodynamics, which governs the flow of energy within the universe, is equally influential. The second law of thermodynamics, which states that entropy always increases, describes how systems move toward greater disorder. This concept governs everything from the cooling of planets to the inevitable formation of black holes, regions of space where matter becomes so dense that not even light can escape. These interconnected laws of physics provide the scaffolding for understanding the birth, evolution, and behavior of celestial bodies throughout the universe. The journey of understanding gravity began thousands of years ago with early thinkers like Aristotle, who postulated that heavier objects fall faster than lighter ones. However, it was not until the 17th century that Sir Isaac Newton revolutionized our understanding with his law of universal gravitation. Newton described gravity as a force that acts across distances, connecting objects as varied as an apple falling from a tree to the moon's orbit around the Earth. His work laid the foundation for classical mechanics, providing an essential framework for understanding gravitational interactions in a way that could predict celestial events with remarkable accuracy. Then, in the early 20th century, Albert Einstein transformed our understanding once again. His theory of general relativity proposed that gravity is not just a force, but the curvature of spacetime itself. Massive objects, like planets and stars, bend the fabric of spacetime, creating paths that other objects follow. This radical shift in perspective not only explained planetary motion, but also predicted phenomena such as the bending of light around large masses, which was later confirmed through observational evidence. Despite these groundbreaking advances, there remain fundamental questions that we have yet to answer. For instance, while we understand the gravitational effects on a cosmic scale, its behavior at the quantum level remains elusive. This gap in understanding is particularly evident in the study of black holes, where the laws of general relativity seem to conflict with the principles of quantum mechanics. The search for a unified theory that can reconcile these two domains remains one of the most tantalizing challenges in modern physics. Moreover, recent discoveries of dark matter and dark energy have only deepened the mystery surrounding gravity. These substances, which account for a significant portion of the universe's mass and energy content, remain invisible to us, not interacting with light or known forms of matter. Understanding how dark matter and dark energy influence gravity and the structure of the universe is a key pursuit in contemporary research, as scientists seek to uncover their roles in shaping the cosmos. As technology continues to advance, so too does our understanding of gravity and the universe. The advent of supercomputing has revolutionized astrophysics, enabling researchers to simulate complex cosmic events that were once beyond reach. These simulations are now more intricate and precise than ever before, allowing scientists to study the behavior of galaxies, stars, and black holes with unprecedented detail. Supercomputers can now model everything from the formation of cosmic structures to the collision and merging of galaxies, providing valuable insights into the evolution of the universe. Perhaps most striking is the ability to simulate supernova, the explosive death throes of stars that create the elements necessary for life. By recreating these cataclysmic events in a virtual environment, scientists can study how stars explode, how elements are synthesized, and how these processes contribute to the larger story of cosmic evolution. These simulations provide an invaluable tool for understanding the universe, offering a glimpse into the forces that shape the very fabric of existence itself. As we continue to push the boundaries of our understanding, we remain driven by the same questions that have fascinated humanity for centuries. What is the true nature of gravity? What lies beyond the edge of the observable universe? And perhaps most tantalizing of all, what does the future hold for the infinite cosmos we call home? The answers, though still out of reach, lie somewhere in the vast expanse of space, waiting to be uncovered by the curiosity and ingenuity of those who dare to ask. The rapid advancement of computational technology has revolutionized our understanding of the cosmos, enabling us to incorporate intricate physical processes into our models with greater precision. Factors once beyond our ability to fully grasp, such as the dynamics of dark matter, the effects of cosmic rays, and the behavior of gases under extreme conditions, are now integrated into our simulations. As we refine these models and enhance their fidelity, the accuracy of our predictions improves, bringing us closer to a more profound understanding of the universe. Ultimately, the relationship between technology and astrophysics is reshaping not just our theoretical frameworks, but also our methods of observation. With more accurate simulations, scientists are better equipped to pinpoint where to focus our telescopes and resources, allowing us to explore the universe with an unprecedented level of precision. Every step deeper into these simulations uncovers new insights, moving us closer to unlocking the mysteries of the universe that have long eluded us. One of the most transformative tools in this quest is artificial intelligence, AI. In the realm of cosmic data analysis, AI has become indispensable, serving as an essential ally for scientists in deciphering the overwhelming amounts of data that flood in from space. The universe, vast and complex, generates data that far exceeds the capacity of any human team to process effectively. From galaxies scattered across the universe to the faint whispers of cosmic microwave background radiation, AI assists in sorting through this data, detecting patterns and signals that might otherwise remain hidden. AI's impact on cosmology is most notable in its ability to classify and interpret celestial phenomena. Take, for example, the discovery of exoplanets. Traditional methods require extensive calculations and significant time to detect planets orbiting distant stars. However, AI algorithms can swiftly analyze the light signals emitted by these stars, spotting the subtle dips in brightness that indicate a planet's transit. This process, once painstakingly slow, is now accelerated, allowing us to identify potential habitable worlds beyond our solar system with remarkable speed and accuracy. Furthermore, AI plays a critical role in managing data from astronomical surveys. Observatories like the Vera C. Rubin Observatory generate vast data sets as they scan the night sky. AI algorithms can automate the detection of transient events such as supernova or gravitational waves by rapidly analyzing images and pinpointing anomalies. This efficiency not only amplifies our observational capabilities, but also increases the likelihood of detecting fleeting cosmic events in real time, events that could have otherwise gone unnoticed. At its core, the intersection of AI and cosmic exploration represents an exciting frontier in our pursuit of understanding the universe. By leveraging the power of AI, scientists are gaining deeper insights into the mechanics of galaxies, stars, and even the fundamental nature of existence itself. As our technological capabilities continue to evolve, the partnership between human intellect and artificial intelligence will undoubtedly illuminate even the darkest corners of our cosmic landscape, helping us to answer questions that have plagued humanity for millennia. Looking toward the future of space exploration, emerging technologies are set to unlock the secrets of the universe, even in its most distant reaches. One of the most thrilling advancements is the development of increasingly sensitive telescopes, which will be equipped with enhanced detectors capable of capturing faint light from stars and galaxies located billions of light years away. With larger mirrors and improved optics, future telescopes will provide us with a level of detail in observing the cosmos that was previously unimaginable. Simultaneously, we are witnessing groundbreaking progress in spacecraft propulsion systems. Traditional rocket technology severely limits the distances we can travel within our solar system. However, innovative concepts such as ion propulsion and solar sails promise to revolutionize space travel, enabling spacecraft to journey much farther and faster than before. Imagine missions that venture to the outer edges of our solar system or even into interstellar space, gathering data from environments that were once considered beyond our reach. These missions could provide invaluable insights into the early solar system and offer new perspectives on exoplanets in distant star systems. As technology advances, the role of artificial intelligence and machine learning in data analysis will become even more pronounced. With the massive influx of data from telescopes and sensors, algorithms will be crucial for processing and interpreting this information more efficiently than any human team could. The result is the rapid discovery of patterns, the identification of celestial phenomena, and the ability to analyze complex data sets faster than ever before. This efficiency will undoubtedly lead to breakthroughs that deepen our understanding of cosmic events and potentially uncover new, unknown phenomena. In parallel, collaborative efforts in space exploration, including international partnerships and private space companies, will further enhance our capabilities. By pooling resources, expertise, and technology, we can launch more ambitious missions, reaching beyond the limits of what any single organization could achieve on its own. The future of space exploration will not only be shaped by the technologies we have today, but also by the innovative breakthroughs that are just around the corner, promising to expand our knowledge of the universe in ways we have yet to imagine. As humanity sets its sights on the stars, it is crucial to consider the ethical implications of exploring and colonizing other planets. While the allure of space exploration is undeniable, we must carefully contemplate the potential consequences of our actions, not only on these celestial bodies, but also on ourselves. One of the primary ethical considerations involves the preservation of extraterrestrial ecosystems. Just as we recognize the importance of protecting our own planet's biodiversity, we must question whether we have the right to disturb or exploit ecosystems on planets that we do not yet fully understand. Another significant ethical concern is the potential for contamination. When we send missions to other planets, especially those that might harbor life, there is always the risk of introducing Earth's organisms into alien environments. This could disrupt or even endanger any native life forms that may exist. As a result, there is an ethical responsibility to minimize our impact on these foreign ecosystems, ensuring that our exploration does not cause irreversible harm. The principle of planetary protection, which guides many current space missions, underscores humanity's obligation to protect the integrity of extraterrestrial environments. Moreover, the prospect of colonizing other worlds raises complex moral and social questions. If we were to establish settlements on planets like Mars, who would control these new territories? Historically, the colonization of land on Earth has led to exploitation, conflict, and injustice. It is essential that we learn from these past mistakes and ensure that space colonization is approached with respect for the rights of any potential future inhabitants and without replicating the injustices of our history. Finally, we must reflect on the motivations behind our cosmic ambitions. Are we driven by a genuine desire to explore and expand human knowledge, or is it simply a quest for resources and territorial expansion? Understanding our true intentions is essential in ensuring that our endeavors in space prioritize ethical considerations, balance exploration with responsibility, and foster a sense of stewardship for the universe. Before we take those monumental steps beyond our planet, these questions must guide our journey. The pursuit of understanding the universe extends far beyond intellectual curiosity. It has profound implications for technological innovation on Earth. As scientists and researchers tackle the immense challenges involved in studying the vast phenomena of space, new technologies emerge that often benefit our everyday lives. Take, for example, the development of powerful telescopes. These require advancements in imaging technology, which often translate into breakthroughs in fields like medicine and telecommunications. Devices such as high-resolution cameras and sensors, which are used in medical imaging systems like X-rays and MRIs, trace their origins back to technologies originally developed for astronomical research. This connection between space exploration and technological innovation is not limited to imaging alone. The demands of space travel have spurred advancements in materials science as well. The need for lightweight, durable materials capable of withstanding extreme temperatures and pressures in space has led to innovations that improve everything from transportation systems to consumer electronics. These technologies are not only pushing the boundaries of what's possible in space exploration, but also creating ripple effects across multiple industries, improving efficiencies and transforming life on Earth. Ultimately, the quest to decode the mysteries of the universe serves as a powerful catalyst for human ingenuity. As we venture further into the cosmos, the technologies that emerge from this exploration reshape our world in ways we never could have anticipated. Each new discovery paves the way for the next, driving an ongoing cycle of innovation that inspires us to dream bigger and reach higher. The future of space exploration is not just about uncovering the secrets of distant stars, but about the transformative technologies that will shape our lives here on Earth.